The arrow of time. The arrow of time is one of the biggest unsolved mysteries in physics. The laws of physics don't care about time's direction, so why does time only move forward? A glass shatters its pieces, scattering across the floor, but they never leap back together. At the microscopic level, the universe doesn't seem to have a preference for forward or backward. The laws governing particles and forces are time reversible. An electron doesn't care if it's moving into the future or retreating into the past. It behaves the same way either direction, and yet here we are moving in one direction, always forward. Why this question has haunted scientists for centuries. Among them was Rudolf Clausius, a 19th century physicist who introduced the idea of entropy, a measure of disorder in a system. A cold glass of water has low entropy. Pour in some hot water and the heat spreads out evenly. That's high entropy. Ropey Clausius realized that in any isolated system, entropy always increases. This became the second law of thermodynamics, one of the most unyielding principles in science. This Clausius realized was the arrow of time. Imagine a perfect cup of coffee, dark liquid, untouched cream. You pour the cream in, and at first it dances beautiful swirling eddies of white and black. But over time, those delicate patterns dissolve into an even brown. The system has gone from order to disorder, from low entropy to high entropy, and there's no going back. But here's the haunting part. If entropy always increases, then at some point it must have been incredibly low. In the earliest moments after the Big Bang, the universe was a staggering portrait of order, balanced on a knife's edge. But why did the universe start in such a bizarrely ordered state? Why wasn't it born chaotic and unstructured? This is where the mystery deepens. Some physicists suggest that the universe itself is an entropy-generating machine. As it expands, new space forms, and with it, more opportunities for entropy to increase like ink spreading on an infinite canvas. But this only explains what happens after the Big Bang. It doesn't explain the universe's initial low entropy state. Others, like physicist Julian Barber, have suggested something more unsettling. Time might not exist at all. Barber envisions the universe as a timeless landscape, a series of frozen moments, like individual frames on an infinite film reel. We perceive them in sequence, but they all exist simultaneously, past, present, and future, locked together in an eternal tableau. If this is true, then time itself, the arrow we cling to so dearly, might be an illusion, a trick of perspective. And then there's the multiverse hypothesis. What if our universe is just one bubble in an endless cosmic foam? In most bubbles, entropy might have started high, and time might not flow at all. Perhaps our universe is a statistical anomaly, an extraordinarily rare pocket of low entropy in a sea of chaos. But these answers feel like whispers in the dark grains of sand slipping through our fingers each. Theory offers a glimpse, but none hold the full picture. Entropy grows, stars burn, galaxies collide, and someday entropy will win. The universe will run out of ways to rearrange itself. Stars will fade into embers, black holes will evaporate, and the cosmos will fall into a silent, cold equilibrium, a state physicists call a heat Death time will stop, not because it's broken, but because there will be no difference between yesterday and tomorrow. Nothing will happen ever again, but that's billions of years away for now. The shattered glass stays broken, the cream swirls into coffee, and tomorrow still waits just out of reach. Time moves forward, carrying us with it, a cosmic river flowing from the improbable order of the past into the chaotic unknown of the future. The arrow of time remains one of the deepest, most unsettling mysteries of our universe, and yet somewhere hidden in the mathematics of entropy, the frozen landscapes of timeless moments, or the chaotic probabilities of the multiverse lies. The answer: matter-antimatter, a matter-antimatter asymmetry, symmetry. The universe as we know it shouldn't exist, not in the way we see it, not with galaxies spiraling through the void, nor stars burning with nuclear fire, nor planets orbiting in serene silence, and certainly not with you, here listening to this story according to the fundamental laws of physics. Every particle of matter, the protons, neutrons, and electrons that make up everything, should have been perfectly matched by its antimatter, twin. A proton mirrored by an antiproton, an L-elon by a positron, and when matter and antimatter meet, they annihilate each other in a burst of pure energy, leaving behind nothing but light. If the universe had followed these rules perfectly, there would have been no planets, no stars, and certainly no life. There would only be a cold, empty void, a silent afterglow of annihilation, but that didn't happen. Something, somewhere broke the balance somehow. Matter won today. We find ourselves standing on the fragile residue of this imbalance for every billion pairs of particles and antiparticles that formed in the earliest moments of creation. One extra particle of matter remained, and from that 1 in a billion imbalance came everything: the galaxies, the stars, the swirling gas clouds, and the atoms in your body. But why? What happened in those first moments of the universe that tilted the scales in favor of matter, and how did such an unimaginably tiny difference lead to everything we see today? To answer this question, we have to travel back, not just to the Big Bang, but to the chaotic, superheated moments that followed. In those first fractions of a second, the universe was a seething, turbulent sea of particles popping in and out of existence. Energy and matter were interchangeable, and symmetry reigned supreme. But as the universe expanded and cooled, something strange happened. Symmetry broke the pristine balance between matter and antimatter was disrupted ever so slightly, and it's in this disruption that the secret of our existence lies. In the 1960s, the Soviet physicist Andrei Sakharov laid out the blueprint for how such an imbalance could have emerged. According to Sakharov, 3 critical conditions needed to be met in those early moments. First, the universe had to allow matter and antimatter to behave differently, a violation of something called CP symmetry. Second, the universe needed to be out of equilibrium, a chaotic state where particles and antiparticles didn't have equal chances to interact. And third, there had to be a way to create more matter than antimatter through these interactions. It sounded simple enough, but actually finding these violations proved far more challenging In 1964, physicists James Cronin and Val Fitt made a discovery that would shake the foundations of particle physics while studying particles called chons. They observed a tiny but unmistakable violation of CP symmetry in certain rare interactions chons, and their antimatter counterparts behaved slightly differently. It was the first hard evidence that nature did have a however subtle, for matter over antimatter, but there was a problem. The CP violation seen in chons was far too small to explain the universe we see today. It was like finding a faint scratch on a massive wall and trying to claim it explained the collapse of an entire building. Clearly, something else was at play. In recent decades, physicists have turned their attention to one of the most elusive particles in the cosmos. The neutrinos are ghost-like particles that barely interact with the rest of the universe. Trillions of them are passing through your body right now unnoticed. Some theories suggest that neutrinos might hold the key to matter-antimatter asymmetry, specifically if neutrinos are what's known as Majera particles, particles that are their own antiparticles. They might have decayed in the early universe in a way that slightly favored matter. This process, known as leptogenesis, could have created the tiny imbalance that eventually led to the universe we see today. But detecting and studying neutrinos is like trying to capture shadows with your bare hands. Experiments deep underground, shielded from the noise of the world above, are carefully watching for the faintest hint of neutrino behavior that could confirm this theory, and yet the answers remain just out of reach. Whispers in the dark hints. In the noise, there's also another idea, one that's as bold as it is unsettling. What if antimatter isn't missing at all? What if it's simply somewhere else? Some physicists speculate that entire regions of the universe could be made of antimatter, galaxies, antimatter stars, and antimatter planets. If these regions exist, they would be separated from matter by vast gulfs of emptiness, because where the two meet, annihilation would light up the cosmos like fireworks. But here's the thing we've never seen: these fireworks. The telltale gamma ray signatures of matter and antimatter colliding on cosmic scales are absent from our observations wherever antimatter went. If it went anywhere at all, it seems to have left no trace. And so the mystery deepens somewhere in the equations of particle physics, in the decays of chons, in the elusive flicker of neuter, or perhaps in the far reaches of the cosmos. The answer is waiting, an answer that could explain not only why matter exists, but why we exist. It's strange to think that our entire universe, the vast galaxies, the burning stars, and the life teeming on our small blue planet owes its existence to an imperfection, a flaw, a tiny imbalance in the machinery of creation. The universe broke its own symmetry, and from that imperfection came everything. But was it truly an accident? Was it a statistical fluke? A cosmic coin flip that happened to land on edge? Or is there something deeper, something fundamental woven into the laws of physics, a reason why the universe preferred matter over antimatter for now? The answer remains hidden, scattered across particle colliders, deep space telescopes, and subterranean neutrino detectors. And with every experiment, every flash of light on a detector screen, we move one step closer to understanding the imbalance that gave rise to everything. One day the universe will give up its secret, and when it does, we'll finally know why there's something instead of nothing. Quantum tunneling at the heart. Quantum tunneling of reality lies a rule book, a set of fundamental laws that dictate how the universe behaves. These laws are steadfast, reliable, and for the most part predictable. Drop a ball and it will fall. Heat flows from hot to cold. A brick wall stops you in your tracks. But beneath this seemingly stable surface, deep in the quantum world, reality starts to misbehave. Particles don't play by the same rules. They flicker, they blur, and sometimes they do something extraordinary. They pass through barriers, as if they weren't even there. This is quantum tunneling, one of the strangest phenomena in all of physics. Imagine standing in front of a mountain. You could spend years trying to climb over it or dig your way under it. But in the classical world, the world of large objects governed by Newtonian physics, you would never expect to. Simply pass through it. Yet, in the bizarre world of quantum mechanics, particles can do just that. Electrons, protons, even entire atoms have been observed performing this impossible escape act. But how does it work? And perhaps more intriguingly, are there limits to this quantum magic? To understand tunneling, we first need to understand how particles behave in the quantum world. In our everyday experience, particles are distinct, well-defined objects. A marble on a table is either here or there. But in the quantum realm, particles behave both like particles and like waves. A duality that defies intuition. Instead of having a single position, a quantum particle exists as a probability wave, a mathematical haze of possible locations. Picture throwing a stone into a pond. Ripples spread out in all directions. In the same way, a quantum particle's wave function spreads across space, representing the probability of finding the particle at different location. Now imagine placing a wall in the path of these ripples. Classically, the ripples would stop at the barrier, but quantum mechanically, the wave function doesn't vanish completely. It leaks through on the other side of the wall. There's still a faint ripple, a tiny probability that the particle could tunnel through the barrier and appear where it shouldn't be. This isn't just abstract theory. Quantum tunneling is the engine behind some of the most important processes in the universe. Inside the heart of stars, hydrogen nuclei overcome their natural repulsion to fuse together, releasing energy in the form of light and heat. Classically, the repulsion between their positive charges should make fusion nearly impossible, but thanks to quantum tunneling, these particles can sneak through their energy barriers, allowing stars to shine here on Earth. Tunneling forms the backbone of technologies like scanning tunneling microscopes, which allow science SSTs to see individual atoms by exploiting the tunneling of electrons. It's also critical in technologies like flash memory, where electrons tunnel through insulating layers to store information in your smartphone or computer. But as miraculous as quantum tunneling seems, it's not without its limits. For tunneling to happen, the barrier can't be too thick, nor can it be too tall. The particle must have some probability of reaching the other side. As the barrier grows taller or wider, the likelihood of successful tunneling drops exponentially. In a sense, Tunneling isn't a cheat code to bypass reality. It's more like rolling an infinite set of dice and hoping for a miracle. And yet physicists are pushing the limits of tunneling in laboratories. Around the world, scientists have managed to tunnel entire molecules and clusters of atoms through barriers stretching the boundaries of what seems possible. But could something larger, a virus, a human cell, or even a full human being ever tunnel through a wall theoretically? Yes, practically, almost certainly not. The wave function of a complex object, like a human, is astronomically tiny. The probability of every single particle in your body coordinating to tunnel simultaneously is so unfathomably low that it borders on the impossible. You'd have better odds of randomly assembling Shakespeare's Hamlet by throwing Scrabble tiles into the air. But even at the microscopic scale, tunneling isn't fully understood. Recently, scientists have been exploring the time it takes for a particle to tunnel. Does it happen instantly, or does the particle actually travel through the barrier step by step? Experiments with ultra-fast lasers suggest that tunneling might happen faster than we ever thought possible, perhaps even instantaneously. But this mystery remains unsolved, lurking at the edge of our understanding. And then there's the question of whether tunneling could reveal something deeper about the nature of reality itself. Could tunneling hint at hidden dimensions? Could it be a sign of physics beyond our current models? Some physicists believe that tunneling might offer a glimpse into the elusive theory of everything, a framework that unites gravity, quantum mechanics, and the cosmos under a single, elegant equation at its core. Quantum tunneling is a reminder of just how strange and wonderful our universe really is. It shows us that at the smallest scales, reality isn't solid or predictable. It's slippery, probabilistic, and deeply mysterious. Particles don't respect boundaries in the way we expect them to. They blur the line between here and there, between what is and what isn't. So the next time you see light from a distant star or store a photo on your phone, remember somewhere, deep in the fabric of reality, particles are breaking the rules. They're sneaking through barriers, defying expectations, and reminding us that the universe is far stranger and far more beautiful than we ever imagined, and perhaps, just perhaps, hidden within the limits of quantum tunneling lies the next great breakthrough in our understanding of reality. The question isn't whether something will tunnel through that final barrier, it's simply a matter of when. Oh my God, particle. Imagine a single, oh my God, particle proton, a subatomic particle smaller than an atom, traveling through the vast emptiness of space. Now imagine that proton moving so fast, with so much energy, that it could knock over a bowling pin from thousands of kilometers away if it ever stopped moving. This isn't science fiction. These particles are real, and they're called ultra-high energy cosmic rays, the fastest and most mysterious messengers in the universe. But where do they come from? How do they gain such extraordinary energy far beyond what we can achieve in our most advanced particle accelerators? And perhaps the most puzzling question of all, why do they seem to defy the known rules of physics? It was the night of October 15th, 1991, when scientists operating the fly's eye detector in Utah recorded something so extraordinary it felt almost like an error. A single cosmic ray slammed into Earth's atmosphere, releasing an energy equivalent to a baseball traveling at 100 km/h. But this wasn't a baseball, it was a single proton, so small it could pass through your body unnoticed. They called it the "oh my god" particle, and for good reason. Its energy was so staggeringly high, over 300 million times more energetic than particles produced in the Large Hadron Collider, that it left physicists stunned, to put it another way. If this proton was scaled up to the size of a tennis ball, it would have been traveling at nearly the speed of light, with the energy of a rifle bullet. But here's where it gets weird. According to our understanding of physics, particles like this shouldn't exist. Cosmic microwave background radiation, the faint glow left over from the Big Bang, should act like a speed bump, draining energy from such particles over long distances, and yet here it was, a single proton, defying every expectation. Where could something like this possibly come from? Cosmic rays are in many ways ghosts. They don't travel in straight lines. They zigzag chaotically through the universe, twisted and deflected by cosmic magnetic fields. By the time they reach Earth, they've long forgotten where they came from, but physicists have a few suspects. One of them is supermassive. Black holes, colossal engines of gravity that lurk at the centers of galaxies. As matter falls into these behemoths, it gets spun around and ejected in colossal jets, traveling close to the speed of light. Could these jets act like cosmic slingshots, hurling particles into space with unimaginable energy? Another suspect is gamma bursts, the most violent explosions in the universe. These bursts are so powerful that for a few brief moments, they outshine entire galaxies. If cosmic rays are being born in these cataclysms, they could carry with them traces of their fiery origin. But here's the problem. Neither theory fits perfectly. The directions these ultra-high energy cosmic rays come from don't always align with known black holes or gamma bursts. It's as if these particles are hiding their origins, slipping through the universe like cosmic assassins, leaving no trace of where they began. And so physicists have built massive observatories, like the Pierre Observatory in Argentina, an array of detectors spanning over 3,000 square km of land. Every so often, one of these ultra-energetic particles crashes into Earth's atmosphere, creating a shower of secondary particles that cascade downward in a brilliant flash detectable by these instruments. But despite decades of observations, the mystery remains. Physics places a theoretical speed limit on ultra-high energy cosmic rays. It's called the Guyan-Zaton-Kussmann limit. According to this principle, any cosmic ray traveling over vast distances should eventually lose energy as it interacts with the cosmic microwave background radiation, the faint thermal glow left over from the Big Bang. In other words, if a particle is too energetic and has traveled too far, it shouldn't have any energy left by the time it gets here. And yet some ultra-high energy cosmic rays seem to have violated this limit. If these particles are coming from nearby sources, we should have found them by now. If they're coming from far away, they shouldn't have this much energy. The universe, it seems, is playing by rules we don't yet understand. Some physicists have started to wonder if ultra-high energy cosmic rays might hint at new physics. something beyond our current understanding of the universe. One theory suggests that these particles might not even be protons, but something more exotic, like strangelets, hypothetical particles made of a type of quark matter. Others propose that they might be leaking in from parallel universes, crossing the thin boundary between realities. And then there's the truly mind-bending possibility that these cosmic rays are revealing flaws in our understanding of space-time itself. Could the universe at its deepest levels have hidden dimensions or physical laws that only reveal themselves at these extraordinary energies? Ultra-high energy cosmic rays are more than just scientific curiosities. They might be messengers carrying secrets written into the universe at its most extreme scales. Each one that crashes into our atmosphere brings with it a whisper from the cosmos, a fragment of a story billions of light years long. But the story remains unfinished. The origins of these particles remain elusive. Their impossible energies remain unexplained, and every time we detect one, we are reminded of how little we truly know about the universe. Maybe the next particle will bring an answer, or perhaps it will only deepen the mystery. For now, the sky remains quiet, scattered with stars, and somewhere out there, hidden in the cold, dark void, another ultra-high energy cosmic ray is already on its way, hurtling toward us with the energy of 1,000 suns, carrying with it a secret we have yet to decode: white holes in the grand theater of the cosmos. Black holes are the most. White holes, enigmatic characters, bottomless pits where gravity reigns. Supreme, and light itself cannot escape. They are cosmic one-way doors, places where time distorts and matter meets an unknowable fate. But what if there was another kind of door, one not for entering, but for exiting, a mirror image of a black hole, a theoretical object where nothing can go in, only out? These hypothetical objects are called white holes. At first glance, white holes sound more like science fiction than science. They are mathematical predictions, cousins to black holes emerging from the same equations of Einstein's general relativity. But while black holes are well observed across the universe, white holes remain elusive, perhaps non-existent, and yet they remain one of the most tantalizing mysteries in theoretical physics. But to understand white holes, we need to revisit their counterparts. Black holes. In 1915, Albert Einstein published his theory of general relativity, a mathematical masterpiece that redefined our understanding of gravity, space, and time. Soon after, physicist Carl Schwarzschild solved Einstein's equations for a particularly extreme scenario. What happens when a massive object collapses under its own weight, compressing all its mass into an infinitely small point, a singularity? The result was the Schwarzschild metric, the first mathematical description of a black hole. But buried within this solution was something strange, an equally valid yet almost alien second solution. It described an object with reverse Tim-Leakey properties. Instead of pulling everything in, this object pushed everything out instead of being a cosmic trap. It was a cosmic fountain. The Schwarz SH solution had unintentionally predicted white holes, but while black holes arise naturally from collapsing stars and observational evidence surrounds us, white holes have a fundamental problem. They seem impossible to create. A black hole is born from collapse when a star burns through its fuel and gravitational forces crush it into an infinitesimal singularity. But for a white hole to exist, it would have to emerge already formed fully intact, with nothing ever having entered it. Unlike black holes, which devour everything in their path, a white hole would be eternally sealed from the outside universe. It's like seeing a waterfall flowing upward in the real universe. White holes seem forbidden by the second law of thermodynamics. This law dictates that entropy, the measure of disorder, must always increase. A white hole constantly spitting out matter and energy in an orderly manner would represent a universe where entropy decreases, and that simply doesn't happen. And yet the mathematics stubbornly insists that white holes are possible. Gamma ray bursts, short, intense flashes of high energy, radiation, are among the most energetic events in the universe. They are so brief, so powerful, and so mysterious that scientists still don't fully understand what causes them. Some researchers have speculated, could gamma ray bursts be the final size of white holes? Could these sudden chaotic emissions represent the last escape of matter from an impossibly ancient white hole, one that's collapsing or vanishing into non-existence? It's speculative, very speculative, but the connection isn't entirely absurd. After all, if white holes exist, their signatures would be explosive, unpredictable, and unlike anything we've seen before. Here's where things get even stranger. What if black holes and white holes aren't separate entities but two sides of the same coin, a bridge, a wormhole connecting a black hole's singularity to a white hole's outflow in another region of the universe, or even in an entirely different universe? This idea comes from the Ein-Rosen bridge, a theoretical shortcut through space-time, predicted by relativity. In this scenario, every black hole would have a white hole, twin connected through a wormhole. But there's a catch. These connections are inherently unstable. The slightest disturbance, say a single stray photon, would cause the wormhole to collapse instantly, sealing off any potential passage. And yet the image remains haunting, a cosmic bridge where M swallowed by a black hole emerges somewhere, sometime from a white hole. There's another idea equally bizarre. Black holes aren't eternal, they evaporate over time. Thanks to Hawking radiation, a slow, ghostly process where energy leaks away from the black hole's event horizon as a black hole shrinks closer and closer to nothingness. Could it eventually reverse? Could the final moment of a dying black hole trigger the birth of a white hole, ejecting its trapped contents back into the universe in one last chaotic burst of energy? It's an idea that blends black holes, white holes, and quantum physics into one breathtaking possibility. At its core, the white hole problem might not be a problem of relativity at all, but a problem of quantum gravity, the elusive theory that unites Einstein's grand cosmic scales with the microscopic unpredictability of quantum mechanics. Some physicists speculate that white holes might exist in the quantum realm on unimaginably small scales, flickering in and out of existence, tied to the strange foam-like texture of space-time itself. They could be remnants of the early universe, tiny echoes of the Big Bang scattered throughout reality, But without a theory of quantum gravity, these ideas remain shadows on the wall of our ignorance. After a century of speculation, white holes remain trapped in the realm of theory. They are mathematical, echoes, beautiful, but intangible, carved into the equations of our universe, but absent from our telescopes. Perhaps they're impossible, prohibited by the fundamental laws of nature, or perhaps they're out there hidden beyond the cosmic horizon, fleeting and rare, waiting for us to find them. But even if white holes never exist in our universe, their mathematics still teaches us something profound. The universe is not just strange, it's stranger than we can imagine. And somewhere in the equations of relativity, in the whispers of gamma bursts, or in the dying breath of an evaporating black hole, the answer might be waiting for now. The mystery of white holes remains an open door, one we cannot yet step through. Dark matter and dark energy in dark matter and dark energy, the grand expanse of the cosmos, amidst the glittering tapestry of stars and galaxies. There exists an unseen force, a shadowy presence that dominates the universe. It doesn't shine, it doesn't reflect light, and it doesn't interact with the world in any familiar way. Yet without it, galaxies would fly apart. Stars would scatter into the void, and the universe as we know it would collapse into chaos. This invisible force is dark matter, and as if that weren't strange enough, there's something even more elusive lurking in the vastness of space, a mysterious energy that pushes galaxies apart, stretching the very fabric of reality. We call it dark energy. Together, dark matter and dark energy make up over 95% of the universe. Everything we can see, the stars, the planets, the gas clouds, every atom and photon accounts for less than 5%. The rest is darkness, not the comforting shadow of night, but an inscrutable, all-encompassing mystery woven into the structure of existence itself. The story of dark matter begins nearly a century ago with an astronomer named Fritz Zwicky in the 1930s. Zwicky was studying the Coma Cluster, a massive collection of galaxies bound together by gravity using Newton's laws of motion. He calculated how fast these galaxies should be moving based on the visible mass of the cluster, the stars, the gas, and in everything they could observe. But something didn't add up. The galaxies were moving far too fast. By all accounts, they should have flown apart, scattering into the cold void of space, and yet they stayed together as if bound by some unseen gravitational hand. Zwicky proposed the existence of something he called dunkel materie, dark matter, an invisible substance exerting gravitational pull, holding the galaxies in place. At first, few took him seriously, but decades later, astronomer Vera Rubin would uncover striking evidence to support Zwicky's idea, studying the rotation curves of spiral galaxies. Rubin noticed something bizarre, according to Newtonian physics. Stars on the outskirts of a galaxy should orbit more slowly than those near the center, much like planets in our solar system, but they didn't. The stars at the edges moved just as fast as those closer, in defying all expectations. The only explanation was an unseen mass, a halo of dark matter enveloping the galaxy, its gravitational influence stretching far beyond the visible stars. But what is dark matter, despite its profound influence on the universe? We still don't know. It doesn't emit light. It doesn't absorb it, and it doesn't collide with normal matter. Scientists believe it might be made of exotic particles, WIMPs, weakly interacting massive particles, or axions, hypothetical entities that interact only through gravity and the weak nuclear force. Experiments deep underground and in massive particle colliders are searching for these elusive particles, but so far dark matter remains a ghost in the machine, and yet the mystery deepens, because if dark matter is the hidden scaffolding that holds galaxies together, dark energy is the invisible hand pulling them apart in the late 1990s. Two teams of astronomers studying distant type 2A supernova made a startling discovery. They expected to find that the expanse expion of the universe was slowing down over time as gravity pulled galaxies back together. Instead, they found the opposite. The universe isn't just expanding, it's accelerating. Something is counteracting gravity on the largest scales, driving galaxies apart at ever-increasing speeds. This repulsive force is what we call dark energy, and it accounts for nearly 70% of the total energy density of the universe. Its discovery shattered our understanding of cosmology and raised a question that still haunts physicists. What is dark energy? One idea ties it to vacuum energy, a property of empty space itself. Quantum mechanics tells us that even a perfect vacuum isn't truly empty. It's a frothing sea of virtual particles constantly appearing and vanishing. This energy, though minuscule, might add up across the vastness of space, creating a cosmic push that drives the universe apart. Another theory links dark energy to Einstein's cosmological constant, a term he once introduced and later dismissed as a mathematical fix in his equations of general relativity, but with the discovery of an accelerating universe. This constant suddenly became one of the most important numbers in physics. Yet, when physicists tried to calculate its value using quantum theory, they arrived at a number 120 orders of magnitude too large. It's one of the greatest mismatches in all of science, a discrepancy so vast it's been dubbed the vacuum catastrophe. Some physicists suggest that dark energy isn't a constant at all, but a dynamic, evolving field, something they call quintessence. Unlike a fixed cosmological constant, quintessence could change over time, subtly influencing the fate of the cosmos. But for now, these are just theories. Whispers in the dark together. Dark matter and dark energy paint a picture of a universe that is both majestic and profoundly alien. They remind us of how much we still don't understand, that the cosmos is far stranger than our ancestors could have ever imagined. And yet, despite the mystery, we can measure their effects. We can see the gravitational pull of dark matter in the way galaxies cluster together. We can observe the cosmic expansion driven by dark energy in the red shift of distant light. These invisible forces shape the universe, sculpting galaxies, dictating cosmic fates, and setting the stage for everything we see. But the story isn't over. The search for dark matter particles continues in underground labs where detectors sit, patiently waiting for a single elusive particle to leave its mark. Astronomers peer deeper into space, searching for the faintest clues about dark energy in the light of distant stars and galaxies in. The in dark matter and dark energy remind us of a humbling truth. The universe is not what it seems, most of it exists beyond the veil of our senses in realms of darkness that we are only beginning to explore. But perhaps the most profound question isn't what dark matter and dark energy are, but why they exist at all. Why does the universe have this delicate balance, a cosmic tug of war between invisible forces that hold it together and those that tear it apart? Maybe the answers are waiting for us in the depths of space, in the hum of gravitational waves, or in the quiet stillness of a particle detector buried deep underground. Or maybe, just maybe, the universe will guard its secrets a little longer. For now, we're left with this: a cosmos dominated by shadows, by forces we cannot see but cannot ignore. And in those shadows, hidden behind veils of mystery, lies the key to understanding not just the universe, but our place within it, in the vast expanse of space, amidst the silent dance of galaxies and the infinite stretch of the void. The universe holds its breath, and somewhere in the flicker of starlight and the hum of distant quasars, the answers await, waiting for us to notice the nature of dark flow. The nature of dark flow universe, vast and unyielding, stretches beyond our gaze into an endless ocean of stars and voids. Its scale defies comprehension, its secrets buried deep in cosmic shadows, and yet despite all we've uncovered, there's one whisper from the COSOS that refuses to fade, a faint but persistent pull, like an invisible tide, dragging entire clusters of galaxies in a single, unyielding direction. This phenomenon is known as dark flow, and it challenges not just our understanding of gravity, but the very fabric of reality itself. In the grand tapestry of the cosmos, galaxies are not scattered randomly. They flow, they drift, they falter towards gravitational wells, the invisible scaffolding of dark matter and cosmic structures. Most of these motions can be explained by what we call the cosmic expansion, driven by dark energy. But in 2008, scientists examining data from NASA's Wilkinson Microwave Anisotropy Probe, WAP, stumbled upon something unexpected: a subtle but measurable motion of galaxy clusters all drifting in one direction, like leaves caught in a river current. This wasn't supposed to happen, according to our best models of the universe. The distribution of galaxies at this scale should be random, their movements dictated only by local gravitational influences and the gradual stretching of space itself. Yet here was evidence of something more, something pulling entire regions of the observable universe towards an unknown destination. The discovery sent ripples through the scientific community. If dark flow was real, it suggested something lurking beyond the cosmic horizon, something we cannot see, cannot measure, but can still feel. Imagine standing on the shore of a vast ocean, watching the waves move, not with the wind, but towards a distant point beyond the horizon. You cannot see what's causing the waves, but you know something is there, something immense, something hidden. But let's pause for a moment. How did we even measure this drift? After all, galaxies are unimaginably far away, and their motions are influenced by countless gravitational tugs and cosmic forces. Scientists turned to the sun. Zeldovich effect, a subtle distortion in the cosmic microwave background, radiation caused by the hot gas within galaxy clusters. By measuring these tiny distortions, astronomers could infer the motion of galaxy clusters against the faint afterglow of the Big Bang itself, and the result was unmistakable. Clusters of galaxies spread across billions of light years were drifting in the same direction at incredible speeds up to 1,000 km per second, a flow so vast, so consistent, that it couldn't be dismissed as statistical noise or observational error. Something massive, something beyond our observable universe, seemed to be pulling on these clusters with gravitational fingers we cannot see. Theories began to emerge. Some scientists proposed that dark flow might be caused by a colossal structure beyond the observable edge of the universe, perhaps an unimaginably massive supercluster or even a remnant of a previous universe bleeding into ours. Others speculated that it could be evidence of extra dimensions, with gravity leaking through the thin boundaries of our four-dimensional reality. And then there was the most mind-bending idea of all, that dark flow might point towards a multiverse, a collision between our universe and another hidden beyond the veil of cosmic expansion. But here's where things get even stranger. The universe, as we understand it, has a horizon, a limit to what we can observe. Light can only travel so far in the finite age of the universe, years and beyond. That horizon lies nothing we can see, and yet dark flow suggests that this horizon is not the edge of reality, it's merely the edge of our perception. This raises profound questions. Are we seeing the faint, gravitational echo of something truly colossal beyond our cosmic bubble? Is our universe just one droplet in an endless cosmic sea, each droplet influencing the next in unseen ways? And if so, what does that mean for our place in the cosmos? Are we passengers on a drifting ship carried along by unseen tides towards an unknowable destination? Not everyone agrees on dark flow. Follow-up studies using data from newer observatories like Planck have questioned the strength of the evidence. Some scientists argue that what we're seeing might be an artifact, an illusion caused by statistical noise or observational biases. Others remain convinced that the drift is real even if we cannot yet fully explain it. But perhaps the greatest mystery of dark flow isn't whether it exists or not. It's what it represents. If real dark flow tells us that our universe is not isolated, it is not a closed bubble of stars and galaxies drifting quietly into the void. Instead, it suggests connections, threads reaching beyond our universe, tied to something larger, something older, something we cannot yet comprehend. Think about this for a moment. Every galaxy, every star, every planet, including our own, is part of this motion. We are not static observers in a fixed cosmos. We are participants in a grand celestial current carried along by forces older than time towards a destination hidden beyond the limits of light and space. And maybe we'll never know the answer. Maybe the source of dark flow will forever remain veiled behind the cosmic horizon. Or maybe one day new telescopes, new experiments, and new theories will allow us to peer just a little further to glimpse what lies beyond. Until then, dark flow remains a riddle wrapped in gravity hidden in shadows and etched into the motion of galaxies across billions of light years. It's a reminder of how much we still don't know, of how small we are, and yet how profoundly connected we are to each other, to the stars, and to whatever waits. Beyond the edge of the universe, in the end, dark flow isn't just about clusters of galaxies drifting across the void. It's about the pull we all feel, the pull towards the unknown, the unexplored, the unanswered. It's about the human drive to chase horizons, to ask questions, and to follow the faintest whispers from the cosmos. So we drift, all of us together, carried along by currents we cannot see, towards a destination we cannot know, and somewhere beyond the edge of light, the universe holds its breath, and fifth force of nature waits. The fifth force of nature, somewhere in the labyrinthine depths of our universe, hidden in the intricate dance of particles and forces. There might be something more. For centuries, physicists have built a grand cosmic stage, supported by four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Together, they dictate the behavior of everything from the swirling galaxies above us to the trembling atoms beneath our feet. And yet, despite their undeniable success in explaining so much of reality, these four pillars of physics leave gaps, questions unanswered, phenomena unexplained. Could there be a fifth force of nature? The search for this elusive fifth force didn't begin with futuristic particle colliders or sophisticated computer simulations. Instead, it began with something older: gravity. At the start of the 20th century, Albert Einstein shattered our understanding of gravity with his theory of general relativity, revealing it not as a force in the traditional sense, but as the curvature of space-time itself. Yet as powerful as Einstein's equations are, they coexist uneasily with the smallest scales of the universe, where quantum mechanics reigns supreme. In the quantum realm, gravity seems almost out of place, like an old act trying to fit into a modern play. Physicists soon realize something troubling. Our best theories of the large general relativity and the small quantum mechanics simply refuse to speak the same language, and in this silence, this chasm between the cosmic and the quantum, the whispers of a fifth force began to emerge in 2015, deep within the walls of the Atomy Institute in Hungary. A team of physicists led by Tilla Kroer stumbled upon something extraordinary while studying the decay of an excited Barium-8 nucleus. They observed an unexpected anomaly, a tiny blip in the data suggesting the presence of a new particle. This particle, if real, could be evidence of something revolutionary, a force-carrying bond potentially associated with a fifth fundamental force. They named it the X17 particle, a hypothetical boson with a mass of about 17 mega-electron volts. Its existence, if confirmed, could imply an entirely new force, a force that subtly influences matter in ways we've never observed before. But skepticism runs deep in science, and extraordinary claims require extraordinary evidence. If the X17 particle represents a fifth force, what kind of force would it be? Some physicists suggest it might act like a bridge between the known and the unknown, a dark force interacting primarily with dark matter, that mysterious invisible substance that makes up about 85% of the universe's mass in this scenario. The fifth force wouldn't just change our understanding of the atomic world, it could illuminate one of the darkest corners of cosmology. But the implications stretch even further. A fifth force might explain anomalies in galaxy, rotation curves, strange discrepancies in gravitational lenses, or even the subtle drift of cosmic expansion. It might unify seemingly disconnected threads of physics, stitching together a more complete tapestry of reality. Yet the search for this force is fraught with challenges. The anomaly observed at Atom Key has yet to be independently confirmed, and the particle itself remains stubbornly elusive. Other experiments using tools like the Large Hadron Collider or precision atomic clocks are on the hunt, scanning the subatomic world for traces of this ghostly force. So far, they found nothing conclusive, but science thrives on the edge of the unknown. The history of physics is littered with ideas that once seemed outlandish. The curvature of space-time, the uncertainty principle, the wave-particle duality of light. Each discovery began with an anomaly, a faint signal whispering from the depths of data, inviting scientists to lean closer, to question, to doubt, and to explore. If a fifth force truly exists, it could rewrite the fundamental laws of nature. It might require new mathematics, new experiments, and perhaps even a new way of thinking about reality itself. But perhaps more importantly, it would remind us of something essential, that the universe is still hiding secrets in plain sight, waiting for us to notice. For now, the fifth force remains an open question, a tantalizing mystery at the edge of science, somewhere in the flickering glow of particle collisions or the distant dance of galaxies. The answer waits, and whether it reveals itself tomorrow, a decade from now, or centuries in the future, one thing is certain: the universe has not finished surprising us. It never does. The holograph grace principle. The holographic principle: imagine for a moment that everything you know, the stars, the galaxies, the planets, even yourself, isn't quite what it seems. That the universe in all its infinite beauty and complexity might not be a three-dimensional expanse stretching into infinity, but instead something far stranger, something flat, a two-dimensional canvas upon which reality itself is merely projected like light shining through film onto a theater screen. This isn't science fiction. This is the holographic principle, one of the most profound and mind-bending ideas ever. Conceived in theoretical physics, it's a concept that sits at the intersection of black holes, string theory, and the very fabric of space and time. And it all starts with an unsettling realization about information and the strange behavior of black holes. But let's not get ahead of ourselves to understand how physicists stumbled upon this principle. We need to start at the edge of a black hole. In 1974, physicist Stephen Hawking made a groundbreaking discovery. He showed that black holes aren't entirely black. They emit faint radiation, now known as Hawking radiation. Over time, this radiation causes the black hole to shrink and eventually evaporate entirely. But this discovery brought with it a troubling paradox. What happens to the information contained within everything that falls into a black hole? In our universe, information isn't supposed to disappear. If you burn a book, its pages might turn to ash. But the information, the words, the ink, the arrangement of letters isn't truly destroyed. In principle, you could piece it all back together from the smoke, heat, and ash. If you had enough knowledge and computing power, this idea is deeply embedded in the laws of physics. Information cannot be lost, and yet if a black hole evaporates completely, where does all that information go? This puzzle is known as the black hole information paradox, and for decades it haunted physicists. Among them was Gerard THFT, a Dutch theoretical physicist who would go on to win the Nobel Prize in the 1990s. 'Hoof proposed something radical. Maybe the information that enters a black hole isn't lost. Maybe it's stored on the event horizon, the boundary of the black hole itself. Imagine a three-dimensional object falling into a black hole. Its information, instead of vanishing into the singularity, gets encoded on the surface of the event horizon, like a shadow projected onto a wall. This realization was profound. It suggested that everything happening inside the black hole could, in principle, be described by data imprinted on its two-dimensional surface. But what if this wasn't just true for black holes? What if it was true for the entire universe? Enter Leonard Susskind, a theoretical physicist who expanded on T. Hoff's idea. Susskind proposed that the universe itself might operate under a similar principle. Everything we perceive in three dimensions might actually be encoded on a distant, two-dimensional boundary, a cosmic horizon at the edge of our observable universe. To put it simply, our three-dimensional reality might be a hologram now, before your mind starts spinning into existential dread. Let's clarify what this means. The holographic principle doesn't suggest that the universe is fake or an illusion like in the Matrix. Instead, it proposes that the fundamental description of reality might be simpler than it appears, that the vast, seemingly boundless cosmos can be described entirely by information encoded on a two-dimensional surface. But how could this possibly work? How can a two-dimensional surface describe a three-dimensional universe? Think about a holographic image on the surface of a flat, two-dimensional sheet. You can store information that creates the illusion of three dimensions. Walk around a hologram and you can see the depth perspective, even movement. The image isn't in the sheet, it's projected from it in a similar way. The holographic principle suggests that our experience of three-dimensional space, the feeling of depth, distance, and motion, might be an emergent property of a deeper two-dimensional reality. At this point, the principle becomes more than just a curiosity. It becomes a powerful mathematical tool. In 1997, physicist Juan Malcina proposed a groundbreaking theory known as the ADS-CFT correspondence. It provided a concrete example of the holographic principle in action, showing that a universe described by gravitational forces in three dimensions could be mathematically equivalent to a universe described by quantum mechanics in two dimensions, in other words, gravity and quantum mechanics. Two seemingly incompatible theories might actually be two sides of the same holographic coin. This realization sent shockwaves through theoretical physics. Suddenly, the holographic principle wasn't just an abstract idea. It was a framework, a lens through which physicists could attempt to unify the two great pillars of modern science, Einstein's general relativity and quantum mechanics. But here's where things get even stranger. If the universe is indeed holographic, it raises profound philosophical questions. What does it mean to exist in a universe where space and time might not be fundamental, where everything we see, feel, and experience is at its core just information encoded on a distant boundary? It also suggests something deeply unsettling about reality itself. If the universe is fundamentally two-dimensional, then space and time, the very stage upon which all of existence plays out, might not be as solid as we think they might be emergent properties like the shimmering surface of a pond, hiding a far deeper reality beneath. For now, the holographic principle remains a theory, a tantalizing clue in the search for a theory of everything, but experiments like those conducted at the Fermilab Holer are actively trying to find evidence for this holographic nature of reality. Scientists are searching for tiny, jittering fluctuations in space-time, the pixels of our cosmic screen. Whether or not these experiments succeed, the holographic principle has already changed how we think about the universe. It's shown us that the line between dimensions, between space and information, might not be as clear as we once believed. It's a reminder that reality, no matter how familiar it feels, still holds secrets so strange they seem pulled from science fiction. So the next time you look up at the night sky filled with distant stars and galaxies scattered across unimaginable distances, remember this. It's possible that everything you see magnetic monopoles, magnetic fields are everywhere. They guide migrating birds across continents. They shape the glowing auroras dancing in our skies, and they wrap around stars and galaxies like invisible threads. But there's something strange about them, something deeply asymmetrical. Every magnet has two poles, a north and a south. Break one in half, and you won't get a single north or south pole. You'll just have two smaller magnets each with their own pair of poles. No matter how small you cut it, the poles remain inseparable. And yet when physicists write down the mathematical laws of magnetism, there's nothing, absolutely nothing, that forbids the existence of a single, isolated magnetic pole, a magnetic monopole. It's as if the universe is holding on to a secret, a single missing piece in the grand puzzle of fundamental forces. If magnetic monopoles exist, they wouldn't just solve an academic curiosity. They would unlock answers to some of the deepest questions about the nature of reality, and yet despite nearly a century of searching, we haven't found one, not yet. The story begins in the 19th century with James Clerk Maxwell, one of the greatest physicists who ever lived. Maxwell's equations unified electricity and magnetism into a single, elegant theory. They revealed that electric charges, like electrons or protons, can exist on their own. A single electron carries a negative charge. A single proton carries a positive charge. But magma jets, they seemed different. Maxwell's math showed that magnetic poles must always come in pairs, north and south locked together forever. But then in 1931, Paul Dare, a quiet, deeply introspective physicist, noticed something strange while exploring the mathematics of quantum mechanics. Dre discovered that if even a single magnetic monopole existed anywhere in the universe, it would explain one of the biggest mysteries in physics: why electric charge is always quantized. why every electron carries the exact same tiny charge, and why every proton perfectly balances it. Drax. Insight was breathtaking. A single magnetic monopole hiding somewhere in the cosmos could explain a property shared by every charged particle in existence. It was as if the universe had written its deepest rules in invisible ink, and Draw had caught a glimpse of the message. But there was a problem. No one had ever seen a magnetic monopole, and physics, for all its beauty, is still a science. It demands evidence. Decades passed in the 1970s. Theoretical physicists like Gerard Tahu and Alexander Polyakov showed that magnetic monopoles weren't just mathematical curiosities. They were an inevitable prediction of grand unified theories, attempts to combine the electromagnetic weak and strong nuclear forces into one overarching framework according to their equations. Magnetic monopole could have been born in the furnace of the Big Bang, forged in the chaotic moments when the universe was still a molten sea of particles and forces. But if monopole were created in those fiery first moments, where are they now? One possibility is that they're incredibly rare, so rare that they've drifted apart across the expanding cosmos, each one separated by unimaginable distances. Another possibility is that they're heavy, so heavy that our most advanced particle accelerators can't hope to create them. Some estimates suggest a single magnetic monopole could be billions of times more massive than a proton. If one passed through the Earth, it would leave behind an almost imperceptible magnetic fingerprint, a ghostly trail across our detectors. But then something happened on February 14th, 1982. Physicist Blas Cabrera was running an experiment using a superconducting loop, a ring of wire cooled to near absolute zero, designed to detect the faint magnetic signal of a passing monopole. And on that Valentine's Day, the detector blinked just once, a perfect single blip, exactly the kind of signal you'd expect from a magnetic monopole. Passing through it was electrifying. For a brief moment, it seemed like physics had caught a glimpse of something extraordinary, but the signal was never repeated. Other detectors, other experiments. Silence. Cabrera's result remains one of the great anomalies in science, a fleeting whisper of something incredible, or just a glitch, a cruel trick played by the noise in the machine. Today, the search continues. Scientists have built vast arrays of detectors buried deep underground or spread across frozen landscapes, all hoping to catch that unmistakable signature. Some have turned their eyes to the stars, wondering if magnetic monopoles might be trapped in the dense cores of neutron stars or lingering in the fiery remnants of supernova. There's even speculation about monopole stars, hypothetical celestial objects where magnetic charge dominates warping space and time around them. And yet, despite all our efforts, the universe remains stubbornly quiet. No monopole have revealed themselves, but here's the thing. If they do exist, if these particles are real, they could change everything. They might explain the strange symmetry between electricity and magnetism. They could offer clues about the unification of forces, or about the earliest moments of the universe, when space and time were still settling into their current form. They might even tell us something about dark matter, that invisible glue binding galaxies together. It's a strange thought that somewhere out there, Drifting silently through the cosmic void could be a single magnetic monopole, a lone traveler carrying with it answers to some of the oldest questions we've ever asked for now. Our detectors hum quietly in the dark, our equation wait patiently on chalkboards and in journals, and every so often a physicist pauses to wonder if the universe is hiding its secrets just out of reach, or if the answer is already staring us in the face, buried in the noise of the data, waiting for someone to notice if a single magnetic monopole exists. It might already be on its way, hurtling through interstellar space, across billions of light years, passing through stars and planets and comets, carrying with it a secret older than the universe itself, and maybe one day it will pass through one of our detectors, and when it does, the universe will finally answer one of its oldest questions, not with a whisper, but with a single perfect magnetic blip, supersymmetry, in the hidden architecture of reality, where particles, supersymmetry dance, and forces weave the fabric of existence. Physicists have long searched for something profound, something that would bring order to the chaos, simplicity to the complexity, and balance to the universe's most fundamental equations. They've given this elusive idea a name, supersymmetry. At first glance, the universe appears wildly asymmetrical. Matter dominates over antimatter. Galaxies spin with puzzling speeds, hinting at invisible dark matter, and the fundamental forces seem like mismatched puzzle pieces awkwardly squeezed together. But beneath this apparent mess, physicists suspect there might be a deeper harmony, a hidden symmetry connecting every particle in existence. To understand why supersymmetry is such an alluring idea, we need to start with the standard model of particle physics. It's the most successful scientific theory ever devised to explain the universe at its smallest scales. The standard model tells us about quarks, the building blocks of protons and neutrons, leptons, like electrons and neutrinos, and the force-carrying particles such as photons, gluons, and the W and Z bosons. And then there's the Higgs boson, the keystone of the entire structure, responsible for giving mass to everything. But despite its triumphs, the standard model has cracks in its foundation. For one, it doesn't explain dark matter, the mysterious, invisible substance that makes up about 85% of the matter in the universe. It also doesn't account for gravity, the force that holds planets in orbit, keeps stars burning, and sculpts the universe on a cosmic scale. And strangest of all, it predicts a universe balanced on a razor's edge, with parameters so finely tuned that even a slight deviation would render reality unrecognizable. This is where supersymmetry enters the stage. The core idea of supersymmetry is breathtaking in its elegance. It proposes that every fundamental particle we know has a superpartner, a hidden twin with slightly different properties. Fermions, like quarks and electrons, which make up matter, would have bonic superpartners and bosons. The particles that carry forces would have fermionic superpartners. These superpartners even have names. Quarks would have squarks, electrons would have selectron, and photons would have phonos at first. This might sound like a particle physicist's fever dream, doubling the zoo of particles we already know. But supersymmetry isn't just about creating more particles, It's about creating balance, the interactions between particles and their superpartners would elegantly cancel out certain infinities that plague the equations of the Standard Model without supersymmetry. The Higgs boson mass, for example, would spiral into absurdly high values, breaking the mathematical consistency of the theory with supersymmetry. Those infinities vanish, and the equations regain their symmetry. But perhaps the most exciting implication of supersymmetry is its connection to dark matter, if super partners exist. One of them, a stable, electrically neutral particle called the neutralino, could be the elusive dark matter particle scientists have been hunting for decades. If supersymmetry is real, dark matter isn't some abstract mystery. It's a real physical particle drifting silently through the vastness of space, binding galaxies together with its invisible gravity. But there's a problem. Despite decades of searching, we've never seen a single superpartner. The Large Hadron Collider, humanity's most powerful particle accelerator, was supposed to be the key when it was switched on in 2008. Scientists hoped it would smash protons together with enough energy to reveal the faint signatures of supersymmetric particles. But collision after collision, dataset after dataset, nothing. The superpartners remain hidden. If they exist at all, this sense has led to a quiet, existential crisis in physics. Supersymmetry is beautiful, mathematically consistent, and capable of solving some of the universe's most pressing puzzles. But science doesn't care about beauty. It cares about evidence, and so far evidence has been stubbornly absent. Some physicists have adjusted their expectations. Maybe superpartners aren't as light as we thought. Maybe they require even higher energies to reveal themselves. Others suggest that supersymmetry might not be a universal symmetry. It could be broken like a shattered mirror whose pieces still reflect an underlying pattern, and still others are beginning to wonder if supersymmetry, despite its elegance, might simply be wrong. But here's the thing about physics. History has shown us time and time again that nature often hides its secrets. Well, the Higgs boson itself was predicted decades before it was finally discovered. In 2012, neutrinos were once thought impossible to detect, and now, well, we observe them routinely. The universe, it seems, enjoys keeping physicists on their toes, and even if supersymmetry turns out to be incorrect, it has already left its mark. The search for these hidden particles has pushed our understanding of high-energy physics to its limits. It has driven the creation of new technologies, new experiments, and new ways of thinking about the universe. But what if supersymmetry is real? What if deep within the data collected at the Large Hadron Collider, a faint signal is waiting, a signature of a squark, a lepton, or a photino? What if dark matter isn't some esoteric puzzle, but a sea of invisible supersymmetric particles passing through us every second without a sound? The stakes are enormous. If supersymmetry is discovered, it won't just be another footnote in a physics textbook. It will be a revolution. It will mean that the universe isn't chaotic or fragmented, but deeply fundamentally symmetrical. It will mean that dark matter isn't just a theoretical placeholder, but a real and measurable aspect of our reality. Right now, experiments continue. Particle accelerators hum beneath the Earth. Detectors stare into the silence of the cosmos, and physicists wait, hoping for a signal, a flash of insight that could reveal the hidden symmetry beneath it all. Supersymmetry might be out there, just beyond the edge of our current understanding, waiting for us to look a little closer, dig a little deeper, and dream a little bigger. And if it's real, if this symmetry exists, it won't just change our understanding of particles or forces. It will change our understanding of everything, a cosmic truth hidden in the smallest building blocks of reality waiting patiently to be found, universe's existence. Why is there something rather than nothing? It's a universe existence question so fundamental, so colossal, that it feels almost impossible to answer. But it's also a question that whispers to us from the depths of our minds when we stare into the night sky. Every galaxy, every star, every fleeting particle of light, all of it exists, and the sheer fact that anything exists at all might just be the most profound mystery of all at its core. The question challenges everything we know about reality. If the universe is governed by physical laws, where did those laws come from? If the Big Bang marked the beginning of time and space, what came before, and why did the universe emerge in such a way that it allowed matter, galaxies, planets, and ultimately us to even begin approaching this question? We must start with what we know, the Big Bang around 8 billion years ago. The universe exploded into existence from an unimaginably hot and dense singularity in those first moments. Space and time unfurled, energy transformed into matter, and the building blocks of everything began to emerge. But what triggered this event? Was it a random fluctuation in a quantum field? Was it a cosmic inevitability bound to happen given infinite time? Or was it something we can't even begin to comprehend? Physicists often point to the strange world of quantum mechanics for possible answers. In the quantum realm, particles can pop in and out of existence seemingly without cause. Empty space isn't truly empty. It sees with fleeting particles and antiparticles winking into being and then annihilating each other. Could it be that our universe emerged from such a quantum fluctuation, a brief moment of instability in the nothingness? This idea suggests that nothing might not actually be nothing. Instead, it might be a restless sea of potential, brimming with the possibility of universes emerging like bubbles in a cosmic foam. But even if this is true, we're still left with the same question: why does this quantum nothingness exist at all? Some scientists turn to the multiverse theory for answers in this framework. Our universe is just one of countless others, each with its own physical laws, constants, and conditions. Perhaps universes are born all the time, and we simply live in one where the conditions were just right for matter to clump together into galaxies, stars, and life. But this too feels like a kind of cosmic deflection. Why does the multiverse exist? Why is there anything at all? The philosopher Gottfried Wilhelm Leitz famously asked this question in the 18th century, and his answer remains one of the most poetic. He suggested that the universe exists because it is the best of all possible worlds, a creation born from some intrinsic principle of perfection. This view has echoed in modern theoretical physics, where some scientists suggest that the universe's laws are finely tuned because in some way they had to be It's not necessarily design, but rather an inevitability, a mathematical truth woven into the fabric of reality. But there's another possibility, one that's deeply unsettling. What if the question itself is flawed? What if asking why the universe exists is like asking what's north of the North Pole? Some physicists suggest that causality, the idea that every effect has a cause, might not apply to the origin of the universe. Time, space, and cause-effect relationships all began with a big bang. To ask what came before might be meaningless, because before didn't exist yet. Even with this perspective, we're still haunted by the mystery, because behind every scientific answer, every elegant equation, there lies a deeper question. Why these laws of physics and not others? Why this universe and not nothing? Perhaps we'll never have an answer. Perhaps the existence of the universe is an unanswerable question, a cosmic enigma forever beyond our reach. But in some ways, isn't that fitting? The fact that we, as self-aware clusters of atoms, can even ask such a question is astonishing in itself. Our minds, products of stardust and evolution, have reached out across time and space to confront the very mystery of existence. And maybe the question is the answer. The universe exists so that questions like this can be asked, so that consciousness can gaze outward and inward and marvel at the improbable beauty of it all. So why does the universe exist? For now, it remains the grandest question of them all, a mystery written across the stars, carried in the hum of atoms, and reflected in every fleeting moment of our lives. Black hole, singularity, the edges of understanding, where light itself bends into silence, and the known laws of black hole singularity physics collapse under their own weight, lies a boundary, a place both feared and revered by scientists. It's the event horizon of a black hole, a cosmic curtain beyond which reality dissolves into something incomprehensible. But what lies beyond that curtain, what happens deep within the black hole at its very core, the answer, or perhaps the lack of one, brings us face to face with one of the greatest enigmas of the universe. The singularity. The term singularity evokes images of infinite density, unimaginable gravity, and a breakdown of everything we know about space, time, and matter, a place where the equations that describe our universe, the very same equations that let us predict the motion of planets and the behavior of stars, simply stop working. To understand how we got here, we need to step back to 1915, when a man with wild hair and piercing eyes scribbled down an equation that would change our understanding of gravity forever. Albert Einstein's general theory of relativity told us that gravity isn't just a force pulling objects together. It's the curvature of space-time itself, sculpted by the mass and energy of celestial bodies. Planets orbit stars, not because they're being pulled by some invisible thread, but because the star's immense mass creates a dent in the fabric of space, and the planet follows that curve. But Einstein's theory also hinted at something far stranger. If enough mass is packed into a small enough space, space-time would curve so dramatically that it would fold in on itself for forming a black hole, a region from which nothing, not even light, can escape. At the heart of this gravitational monster lies the singularity, according to Einstein's equations. The singularity is a point of infinite density and zero volume, a place where all the mass of the collapsing star is compressed into an infinitesimal point. But here's the problem. Infinity isn't something physics can handle very well. It's like dividing by zero. It's not an answer. It's an error message. The singularity is where our theories break down, where the map ends and the terrain becomes unknowable. And yet, despite its unknowability, the singularity isn't just a mathematical curiosity. It's a real physical consequence of our best theories of gravity. But here's where the story takes a sharp turn into the realm of paradox. You see, if singularities truly exist, they pose a problem so disturbing that physicists gave it a name: the cosmic censorship hypothesis. This idea was proposed by the brilliant physicist Roger Penrose. In 1969, Penrose asked a deceptively simple question: could naked singularities exist? Let me explain. In a typical black hole, the singularity is safely hidden behind the event horizon, that invisible boundary surrounding the black hole. Anything that crosses the event horizon is forever trapped, and no information about what happens inside can escape in a sense. The event horizon acts as a cosmic censor, hiding the singularity from view and preventing its chaos from spilling into the rest of the universe. But what if, under certain conditions, a singularity could form without an event horizon? What if it were exposed, raw, unfiltered, and visible to the universe? Such a naked singularity would mean that the deepest secrets of space-time, the breakdown of physics itself, would be laid bare for all to see. The laws of cause and effect could unravel, and our understanding of the universe might fall apart entirely. Penrose's cosmic censorship hypothesis proposes that nature abhor this kind of chaos, that every singularity must be cloaked behind an event horizon hidden from the rest of the cosmos. In essence, the universe has a self-correcting mechanism to prevent us from peering into its most chaotic and incomprehensible depths. But is this hypothesis true? For decades, physicists have wrestled with this question. Mathematical models suggest that under certain exotic conditions, like highly spinning black holes or specific types of gravitational collapse, naked singularities might form. In fact, some numerical simulations hint that cosmic censorship could be violated if a naked singularity exists. It would be more than just a curiosity. It would be a crack in the foundation of our understanding. It would mean that the universe doesn't always play by the rules we expect. But there's another layer to this mystery. If singularities are where Einstein's equations fail, could they also be windows into a theory of gravity, one that unites Einstein's general relativity with the quantum mechanics governing the tiniest particles in the universe? Physicists have long believed that a theory of quantum gravity, something like string theory or loop quantum gravity, might smooth out the infinities of the singularity, replacing the impossible point of infinite density with something more physically meaningful. But for now, the singularity remains hidden and cosmic censorship remains unproven. Black holes continue to act as cosmic safes, locking away their secrets behind event horizons, daring us to figure out how to pick the lock. In recent years, advancements in observational astronomy have brought us closer to these mysterious giants. The Event Horizon Telescope, captured the first ever image of a black hole's event horizon in the galaxy M87, a glowing ring of light encircling the shadow of something unspeakably dense. But even this monumental achievement is only the beginning. Future telescopes and observatories may allow us to probe the fringes of these cosmic voids, inching closer to answers about what lies at their heart. But here's the thing. The singularity, whether hidden or exposed, isn't just a problem for physicists, it's a problem for us. It's a reminder that there are places where our understanding breaks down, where reality stops making sense, and where the universe seems to whisper, "You weren't meant to see this yet. We can't stop looking," because every time we confront the singularity, every time we challenge the limits of physics and peer into the mathematical abyss, we inch closer to something profound. Something about the nature of space-time, and perhaps even existence itself, are singularities truly hidden behind cosmic veils for forever out of reach. Or will we one day find ourselves staring directly into the raw, unfiltered chaos at the heart of a naked singularity, witnessing the universe laid bare in all its incomprehensible glory? For now, the singularity remains the ultimate mystery, an enigma carved into the heart of gravity, hidden in the darkest corners of space-time. And as long as it exists, as long as that quiet question hangs in the cosmic void, humanity will continue to search, to calculate, and to dream, hoping that one day we'll finally understand what lies beyond the edge of the universe's greatest secret, vacuum catastrophe. In the vast vacuum catastrophe, emptiness of space where stars are scattered like distant lanterns and galaxies drift in the slow dance of cosmic time, there exists something that defies intuition, something so counterintuitive that it has left physicists scratching their heads for decades. It's not a star or a planet, not a black hole or a nebula. No, it's the emptiness itself, the vacuum of space, and it holds within it one of the greatest mysteries in modern physics. This enigma is known as the vacuum catastrophe, or more formally, the cosmological constant problem. It's a paradox so profound that it challenges our very understanding of reality. To understand this problem, we must first ask a deceptively simple question: what is nothing? It seems like a straightforward concept. Nothing is the absence of something, a void, an emptiness, but in physics, nothingness is anything but simple. According to quantum field theory, even the most perfect vacuum, a space completely devoid of matter and energy, is not truly empty. It's a SE ocean of activity, a bubbling froth of virtual particles popping in and out of existence. Particles and antiparticles spontaneously appear, collide, and annihilate in a ceaseless quantum dance, leaving behind fleeting imprints on the vacuum itself. These virtual particles aren't just theoretical, they have measurable effects. The Casimir effect, for instance, demonstrates that two uncharged metal plates placed very close together in a vacuum will feel a tiny attraction, Ive force, pulling them together. This isn't because of some mysterious energy between them, but because the plates are altering the quantum froth of the vacuum, creating an imbalance of virtual particles. If empty space is in fact not empty, then it must have energy, a background hum. A fundamental baseline physicists call this the vacuum energy, and this energy, strange as it sounds, has consequences on a grand cosmic scale. In 1917, Albert Einstein, in his attempt to describe the universe as a static, unchanging entity, introduced a term into his equations, the cosmological constant. This constant represented a repulsive force embedded in the fabric of space itself, counteracting gravity to keep the universe from collapsing in on itself. Einstein later called it his greatest blunder. After Edwin Hubble discovered that the universe wasn't static, it was expanding, and yet decades later, the homological constant would return this time as an answer to a far stranger mystery. In the late 1990s, two independent teams of astronomers studying distant supernovae made a shocking discovery. The universe isn't just expanding, it's accelerating. Galaxies are not only drifting apart, but are doing so faster and faster with time. This discovery turned cosmology on its head. Some invisible force was pushing the universe apart, a mysterious pressure embedded in the vacuum of space. Scientists resurrected Einstein's cosmological constant to explain it, now rebranded as dark energy. But here's where the paradox begins. Physicists turned to quantum field theory to calculate the vacuum energy, the energy of empty space. The result was staggering. Theoretical predictions suggested that the energy of the vacuum should be 120 orders of magnitude larger than what we actually observe. That's a number so incomprehensibly vast that it's equivalent to comparing the size of an atom to the size of the observable universe. In other words, the vacuum energy predicted by quantum mechanics and the vacuum energy implied by the observed expansion of the universe are wildly, catastrophically different. This mismatch is what we call the vacuum catastrophe, arguably the biggest numerical discrepancy in all of science. How could two of our most successful theories, quantum mechanics and general relativity, disagree so violently? This isn't just a math problem, it's a crack in the foundation of our understanding. If the vacuum energy were even slightly different, if it were just a bit stronger or weaker, the universe as we know it wouldn't exist, galaxies wouldn't have formed, stars wouldn't have ignited, and life would never have emerged. It seems as though the vacuum energy has been fine-tuned to an almost impossible degree, a cosmic coincidence that borders on the miraculous. Physicists have proposed many explanations. One idea suggests that our universe might not be the only one. Perhaps we live in a multiverse where countless universes are born with different vacuum energies. In most of them, the vacuum energy might be catastrophically high, ripping matter apart before anything can form. But in our universe, by sheer statistical luck, the vacuum energy happens to be just right. Others suggest that we might be missing something fundamental, a deeper theory of physics that unifies quantum mechanics and general relativity, smoothing out the mathematical inconsistencies and revealing a hidden order beneath the chaos. Some physicists turn to string theory, hoping its complex web of vibrating strings and extra dimensions might hold the key to resolving the paradox, but the vacuum catastrophe remains unsolved. It's as if the universe is holding up a mirror to our ignorance, reflecting back our incomplete understanding of the most fundamental aspects of reality, and yet it's also a reminder of something beautiful, that even the void, even the nothingness of empty space, is rich with mystery and possibility. You might be wondering, does this paradox have practical implications? Or is it just an abstract puzzle for theoretical physicists to lose sleep over? The answer is both. If we can understand the vacuum energy, if we can unlock the secret of the cosmological constant, we might not only resolve one of the greatest puzzles in physics, but also glimpse the deepest workings of the universe itself. Could an understanding the vacuum energy lead to new technologies, to harnessing the fundamental energies of space-time? Could it reveal insights about the ultimate fate of our cosmos? Will the universe expand, forever grow cold, and fade into eternal darkness? Or will something even stranger happen, driven by the unseen forces lurking in the vacuum? For now, the vacuum remains both a void and a paradox, a whispering silence filled with secrets we can barely comprehend. It reminds us that the universe is not merely stars and galaxies, it's also the invisible fabric between them, the spaces where nothing should exist. Yet everything begins. Perhaps the answer to the vacuum catastrophe lies in equations yet to be written or in observations waiting to be made by future telescopes scanning the night sky. Until then, every time we look into the void, we are reminded of the profound mystery that resides not in what we see, but in the spaces in between, in those silent gaps in the shimmering nothingness. The universe hides one of its greatest secrets, and somewhere out there, or perhaps within us, the answer is waiting to be found. Fine-tuning problem at first. Fine-tuning problem. Glance, the universe seemed vast, chaotic, and in different galaxies collide, stars explode, and black holes silently consume whatever ventures too close. But beneath this grand spectacle lies something far stranger, a hidden order, a set of cosmic dials tuned with unimaginable precision. If these dials were adjusted even slightly by the tiniest fraction, the universe as we know it wouldn't exist. No galaxies, no stars, no planets, and certainly no us. This is the fine-tuning problem, one of the most perplexing mysteries in modern physics and cosmology. Why does our universe seem so perfectly set up for life? Is it coincidence, necessity, or something deeper? To understand the fine-tuning problem, we must first confront a profound truth. The laws of physics are not arbitrary. They are mathematical, elegant, and astonishingly precise. They govern everything from the fusion of hydrogen atoms in the heart of a star to the dance of electrons in a molecule of water. But these laws don't exist in isolation. They depend on a set of fundamental constants, numbers that appear in the equations of nature, and determine how the universe behaves. Take the gravitational constant, for example. It determines the strength of gravity, the force that binds stars, planets, and galaxies together. If gravity were just a little bit stronger, stars would burn through their fuel too quickly, collapsing into black holes before planets or life could ever form. If it were weak, stars might never ignite at all, and the universe would remain a cold, dark expanse of scattered hydrogen. Or consider the strong nuclear force which holds protons and neutrons together in atomic nuclei. If this force was slightly weaker, atoms heavier than hydrogen wouldn't form. There would be no carbon, no oxygen, none of the building blocks of life. And then there's the cosmological constant, the mysterious energy that drives the accelerated expansion of the universe. Its value is so unfathomably small, yet so precisely tuned that even a tiny deviation would have caused the universe to either collapse back in on itself or expand so rapidly that galaxies and stars could never form. Each of these constants is like a dial on an impossibly complex control panel, and somehow every single one is set just right. Change any dial by even a hair's breadth, and the universe becomes sterile, lifeless, or non existent. This level of precision raises an unsettling question. Why is this fine tuning just a fluke, a one in a quadrillion chance? Or is there something deeper at play? Scientists, philosophers, and theologians have all grappled with this question, and their answers range from the mathematical to the metaphysical one. Explanation is the anthropic principle. It suggests that we shouldn't be surprised to find ourselves in a universe that supports life, because if the universe weren't fine-tuned, we wouldn't be here to ask the question in the first place. In other words, the very fact that we're here means the universe must have the right conditions for life. But while the anthropic principle is logically sound, it feels unsatisfying. It doesn't explain why the dials are set the way they are. It simply shrugs and says, well, if they weren't, we wouldn't be here. Another idea is the multiverse hypothesis. What if our universe isn't the only one? What if there are countless universes, each with its own set of physical laws and constants? In most of these universes, the dials are set randomly, and the result is chaos, sterility, or instant collapse. But in an infinite sea of universes, there will inevitably be some, perhaps very few, where the conditions are just right. And we, of course, exist in one of those lucky universes. It's an elegant idea, but there's a problem. We have no direct evidence for the multiverse. It's an idea that sits at the very edge of science, balancing precariously between theory and speculation. Yet it remains one of the most popular explanations for fine-tuning among physicists. Then there's another possibility, one that feels almost poetic. What if the fine-tuning of the universe isn't just an accident, but a fundamental aspect of reality? What if the constants of nature are not random at all, but inevitable, woven into the deep mathematical fabric of existence? In this view, the universe couldn't not be fine-tuned, because these constants emerge naturally from some deeper principle, some elegant equation we have yet to discover. This idea suggests that our universe isn't a lucky accident. It's the inevitable outcome of a deeper law, a cosmic symmetry waiting to be revealed. But perhaps the most unsettling possibility is that we might never know, that the fine-tuning of the universe could remain an eternal mystery, a riddle whispered in the void between stars, forever beyond our reach. What's undeniable is this: we exist on a razor's edge. Every breath we take, every star that shines, every moment of existence depends on the delicate balance of these cosmic dials. It's a reminder of how fragile and improbable our universe truly is. A symphony played on the strings of mathematics, with each note perfectly tuned, and yet here we are thinking, wondering, and asking questions about our own existence, some somewhere buried in the equations of physics or hidden in the glow of distant galaxies. The answer might already be waiting, whether it's found in the hum of quantum fields, the vastness of a multiverse, or the elegance of an undiscovered law of nature. The fine-tuning problem challenges us to confront something deeply humbling, that the universe is not just a chaotic accident, but a place of exquisite, almost impossible precision. For now, we can only marvel at the balance, at the knife edge on which reality rests, at the dials perfectly set, as if the universe itself were holding its breath, waiting for us to notice. In the grand expanse of time and space, amidst the glow of stars and the silence of the void, we find ourselves balanced between knowledge and mystery. The fine-tuning of the cosmos isn't just a scientific puzzle, it's a reminder of how rare, how fleeting, and how precious this existence truly is. And maybe the universe fine-tuned itself so that one day, somewhere, on a pale blue dot circling an ordinary star, we would exist to notice quantum measurement problem in quantum measurement problem. The invisible world of the very small, where particles flicker in and out of existence, where probability rules over certainty, and where reality itself seems to play dice. There lies a question so perplexing, so fundamental, that it challenges our deepest assumptions about what it means to observe the universe. It's called the quantum measurement problem, and it isn't just a technical issue for physicists, it's a philosophical puzzle that cuts to the core of reality itself. At the heart of this mystery lies an idea so bizarre, so counterintuitive, that it has baffled scientists and philosophers for over a century to understand it. We must step into the strange world of quantum mechanics, a theory that describes the behavior of particles at the smallest scales, where electrons orbit atoms, photons dance through space, and the classical rules of physics collapse into a haze of probabilities. In the early 20th century, physicists like Neil Bohr, Heisenberg, and Erwin Schrödinger discovered something extraordinary. Particles at the quantum level don't behave like tiny billiard balls bouncing predictably through space. Instead, they exist as probability waves, mathematical clouds of potential outcomes. An electron, for instance, doesn't have a definite position or velocity until we measure it. Before that, it exists in a superposition, a state where it's everywhere and nowhere. At the same time, it's not just a theoretical oddity, it's something we've observed in the lab. Take the famous double-slit experiment, when scientists fired individual electrons at a barrier with two narrow slits. They expected the particles to pass through one slit or the other and create two distinct patterns on the wall behind it. But instead, they saw an interference pattern, as if each electron was behaving like a wave and passing through both slits simultaneously. But here's where things get really strange. When scientists placed a detector near the slits to see which slit each electron passed through, the interference pattern disappeared. The electrons stopped behaving like waves and started behaving like particles, choosing one slit or the other. It was as if the act of observation itself forced the electron to make up its mind. And this is the crux of the quantum measurement problem. How does the act of measuring or observing a quantum system cause it to collapse from a wave of probabilities into a single, definite outcome? What is observation in this context? Is it the act of a conscious mind looking at the system? Is it the interaction with a measuring device? Or is there something deeper at play? Something woven into the very fabric of reality to make sense of this puzzle? Physicists have proposed various interpretations, each one more thought-provoking than the last one. Of the earliest is the Copenhagen interpretation championed by Niels Bohr and Vera Heisenberg. According to this view, quantum systems don't have definite properties until they're measured the way cave function. The mathematical description of a quantum state represents all possible outcomes until measurement forces one possibility to crystallize into reality. But this raises an uncomfortable question. What counts as a measurement? Is it a human mind, a machine, or simply any interaction with the environment? In 1935, Erving Schrödinger highlighted the absurdity of this interpretation with his now famous thought experiment, Schrödinger's cat. Imagine a cat sealed in a box with a vial of poison that will be released if a radioactive atom decays a quantum event governed by probability according to the Copenhagen interpretation until we open the box and observe the cat. It exists in a superose both alive and dead at the same time. It's an unsettling image, but it captures the essence of the problem. How does the blurry uncertainty of the quantum world resolve into the sharp, definite reality we experience? Then there's the many worlds interpretation proposed by Hugh Everett III in the 1950s. This idea suggests that every time a quantum measurement is made, the universe splits into multiple parallel realities, one for each possible outcome. In one universe, Schrödinger's cat is alive; in another, it's dead. According to this view, the wave function never truly collapses. It simply branches into an infinite multiverse. It's an elegant solution, but it comes at the cost of introducing countless unseen universes, each carrying its own version of reality. Other interpretations, like the pilot wave theory or the quantum decoherence theory, attempt to sidestep the measurement problem in different ways. Decoherence, for example, suggests that interactions with the surrounding environment lock quantum systems into definite states, removing the need for an observer. But even this explanation raises new questions about the nature of measurement and reality at its core. The quantum measurement problem isn't just about electrons, slits, or mathematical equations. It's about the boundary between the quantum world and the classical world, the blurry line between probability and certainty, between potential and actuality. And somewhere along that boundary lies the answer to one of the deepest questions in science. What is reality made of? The implications of this puzzle go beyond physics. They touch on philosophy, on consciousness, on the very act of perception itself. When you look at the stars in the night sky, are you collapsing their quantum states into definite positions? Are you in some profound way participating in the creation of the universe just by observing it? For now, the quantum measurement problem remains unsolved, but every time a physicist fires electrons through slits, every time a quantum computer manipulates entangled particles, every time we probe the fabric of space-time for answers, we edge closer to the truth. Perhaps the universe itself is a kind of grand quantum experiment, a cosmic double slit test waiting for someone somewhere to observe it, or perhaps the answers lie not in the stars or the atoms, but in the space between them, in the fragile act of measurement, where the infinite possibilities of the quantum world collapse into the fleeting certainty of now. One day, we may understand why observation changes reality, why particles choose paths, and whether the universe branches into infinite possibilities or simply shrugs and resolves itself into one. Until then, the quantum measurement problem stands as a reminder that at the smallest scale of reality, certainty is an illusion, and knowledge is always just beyond our grasp. But isn't that the most beautiful mystery of all? That somewhere in the shimmering haze of probability, reality itself is still waiting to be measured. Multiverse hypothesis. The multiverse hypothesis. Universe is vast, so vast in fact that our minds struggle to grasp its scale. Trillions of galaxies, each with billions of stars spread across an unfathomable cosmic expanse. And yet even this staggering immensity might just be a fraction of the whole story. What if our universe isn't the universe? What if it's just one tiny bubble in an infinite ocean of universes each, with its own laws of physics, its own dimensions, its own strange reality? This is the multiverse hypothesis. The idea that our universe isn't alone, but merely one chapter in an endless cosmic anthology. But where did this idea come from? How did scientists, rational thinkers, grounded in observation and mathematics, arrive at such an extraordinary concept? It began with an unexpected twist in cosmology, inflation theory. In the early 1980s, physicist Alan G.T.H. proposed a radical idea to solve some of the most puzzling questions about the universe's early moments according to Girth in the first fraction of a second after the Big Bang. The universe underwent an unimaginably rapid expansion, a brief period of inflation where space itself grew faster than the speed of light. Inflation explained why the universe looks so uniform on large scales, why distant regions of space have nearly identical temperatures. Despite never having been in contact, it was elegant, it was powerful, but inflation also carried a peculiar implication. It might never have stopped in Guth's model. Inflation isn't a one-time event, it's a perpetual process. Pockets of space stop inflating and form stable universes, like bubbles popping in boiling water, but the larger cosmic soup keeps expanding endlessly, generating more and more bubbles, each one a separate universe with its own properties, its own physics. In this view, our universe is just one bubble in an infinite cosmic foam, but inflation isn't the only doorway into the multiverse. Quantum mechanics, the branch of physics governing the tiniest particles in existence, offers another glimpse into this bewildering possibility. In the 1950s, physicist Hugh Everett proposed the many worlds interpretation of quantum mechanics. At its core lies a deeply unsettling idea. Every time a quantum event occurs, the universe splits into multiple branches, each representing a different outcome. Imagine flipping a coin in one universe. It lands heads in another, tails every interaction, every choice, every quantum possibility creates a branching path leading to countless parallel universes, each as real as our own. In one universe, You decided to stay home today. In another, you went outside and met a star ranger who changed your life forever. It's dizzying, it's almost incomprehensible, and yet it emerges naturally from the mathematics of quantum theory. Then there's string theory, a framework attempting to unify all the forces of nature into one elegant equation. According to string theory, the universe operates not in 3 spatial dimensions, but in 10 or 11, depending on the variant of the theory. These extra dimensions are hidden, curled up at microscopic scales far beyond our ability to observe. But they're not trivial. They determine the very fabric of our universe, from the strength of gravity to the behavior of subatomic particles. And here's the twist. String theory doesn't predict one universe. It predicts a landscape, a vast cosmic map containing perhaps 10,500 different possible universes, each with slightly different physical laws. Gravity might be weaker in one universe, stronger in another. Stars might not form in some, while others could teem with exotic forms of matter and energy if the multiverse exists. It could explain one of the deepest mysteries in physics. The fine-tuning problem: why are the fundamental constants of our universe, the speed of light, the charge of an electron, the strength of gravity, so perfectly tuned to allow life to exist if any of these values were slightly different? Stars wouldn't form planets, wouldn't orbit, and complex chemistry wouldn't arise. The multiverse offers an answer. It's not that our universe was designed to be perfect, it's that countless universes exist, each with different constants, and we happen to exist in the rare one where the numbers align just right. But here's the problem: how do you prove it? Science thrives on observation, on experiments, on falsifiable issues, but the multiverse by its very nature exists beyond our cosmic horizon. We cannot peer into other universes. We cannot touch them, measure them, or observe them directly. For some scientists, this makes the multiverse hypothesis unscientific, an intriguing story, but not a testable theory. But there are glimmers of hope. Some researchers suggest that if other universes have ever called Ed with ours like soap bubbles merging in a bath, they might leave scars on the cosmic microwave background, the faint afterglow of the Big Bang. Others propose that subtle signatures in high-energy physics, experiments, or anomalies in cosmic radiation might point towards the multiverse. But so far, the evidence remains inconclusive. The multiverse is an idea on the edge of science, a bridge between mathematics, philosophy, and pure imagination. It challenges our most fundamental assumptions about existence. Are we just one universe among countless others? Are there alternate versions of ourselves, living alternate lives in alternate worlds? Or is the multiverse simply an elegant illusion, a mathematical artifact without physical reality? For now, we don't know, but the question lingers. The universe, our universe, feels vast, ancient, and impossibly complex, and yet it might be just one note in a far grander cosmic symphony playing across infinite dimensions and infinite possibilities. The truth of the multiverse remains hidden just beyond the horizon of our understanding, but whether it's science, philosophy, or something in between, one thing is certain: the multiverse hypothesis challenges us to rethink everything we thought we knew about reality, existence, and our place in the cosmos, emergence of consciousness and physics, emergence of consciousness in the vast fabric of the universe, woven from particles, forces, and fundamental laws. There exists one phenomenon so bewildering, so elusive, that it seems to transcend the very framework of physics itself, consciousness that you are experiencing it right now, the hum of your thoughts, the flicker of awareness as you process these words, the undeniable sense of self that feels more real than the atoms making up your body. But here's the puzzle. How does consciousness emerge from lifeless matter, from mere collections of quarks, electrons, and chemical reactions? To tackle this question, we must embark on a journey, one that stretches from the microscopic dance of particles to the colossal machinery of the brain, and finally to the deep philosophical questions about the nature of reality. Physics has given us tools to understand the cosmos, from the fusion of stars to the entanglement of particles across light years. But can it explain the most intimate phenomenon of all, the feeling of being? You at its core? Consciousness feels irreducible. You can break down a star into hydrogen and helium, or a cell into proteins and DNA. But how do you break down a thought, a sensation, the feeling of red, the taste of sweet weakness, the agony of pain? This is the hard problem of consciousness, a term coined by philosopher David Chalmers. It's not about explaining brain activity or neural pathways. That's the easy problem of consciousness. As strange as it may sound, the hard problem asks, why do these physical processes produce subjective experience? Why isn't the universe just a vast, unfeeling machine? Science has made progress on the easy problem. Neuroscience maps brain regions, tracks electrical signals, and decodes the firing of neurons. But despite these advances, we don't know how neural activity transforms into experience. It's as if we can describe every wire and circuit in a computer, but we can't explain why the screen displays an image, instead of just being a complex web of electronics. Some physicists believe that to crack the mystery of consciousness, we might need to reimagine our understanding of reality itself. Theories like integrated information theory propose that consciousness arises when information is meaningfully integrated in a complex system like the brain. Others, like orchestrated objective reduction, suggest that quantum processes inside neurons might play a role, that consciousness could emerge from the quantum realm where particles behave in ways that defy classical intuition. But this raises more questions. Is conscious an emergent property, like the wetness of water arising from hydrogen and oxygen atoms? Or is it something fundamental to the universe, like space-time and gravity? Some thinkers suggest that consciousness might be woven into the very fabric of reality, a primitive property that exists at the deepest level of physics. In this view, every particle might have a sliver of awareness, a tiny fragment of experience. This idea, known as panpsychism, might sound radical, but it's gaining traction among some serious philosophers and scientists. Let's pause for a moment and consider a thought experiment. Imagine an artificial brain, a perfect replica of your own neuron. For neuron, signal. For signal, would it have consciousness? Would it feel joy, fear, or curiosity? Or would it simply be an incredibly convincing machine, a philosophical zombie simulating awareness without actually experiencing it? If the answer is no, that it would lack subjective experience, then we might be missing something fundamental about how consciousness arises. There's also the idea that consciousness and physics are deeply intertwined at the quantum level. Some scientists speculate that quantum entanglement, where particles remain mysteriously connected across vast distances, might mirror the way different regions of the brain synchronize to produce unified experiences. Could consciousness itself be a form of entanglement on a biological scale? It's a tantalizing idea, but one that remains firmly in the realm of speculation. At the other end of the spectrum lies an unsettling possibility. What if consciousness is simply an illusion, a trick played by our brains, a convenient evolutionary adaptation to help us survive? Could it be that our sense of self, our thoughts, and our emotions are nothing more than the flickering of neurons, a shadow play with no deeper meaning? Some scientists embrace this view, arguing that consciousness is not something to be explained, but something to be seen through, like a mirage on a hot desert road. But then you are still here, listening, experiencing, feeling. Whatever the ultimate nature of consciousness may be, it is undeniably real to you, and that's the paradox. It's both the most immediate and the most mysterious aspect of our existence. If we are ever to understand consciousness, physics and neuroscience may need to join forces with philosophy, computer science, and perhaps disciplines we haven't even invented yet. Maybe the answer lies in a yet undiscovered law of nature, a principle as profound as relativity or quantum mechanics. Or perhaps we're not equipped to answer this question at all, that the key to consciousness is locked in a room we can never enter. But one thing is clear understanding. Consciousness isn't just about solving a scientific puzzle. It's about understanding ourselves, our place in the universe, and the very nature of reality, whether it's an emergent phenomenon, a quantum property, or a fundamental aspect of existence. Consciousness remains the universe's greatest enigma, a mirror reflecting back not just the cosmos, but the deepest questions about what it means to be. So we leave this question hanging in the air as it has hung for centuries. What is consciousness? Is it a trick of physics, a spark of something divine, or the most fundamental layer of reality itself? Perhaps the answer lies within us, waiting patiently somewhere between a firing neuron and a fleeting thought. Theory of everything at the heart of every scientific question, hidden beneath layers of equations and galaxies, there exists a single tantalizing dream, a dream of absolute unity, a dream that somewhere in the deep mathematical fabric of reality lies one equation, one elegant idea that can describe everything, every star, every atom, every force, every fleeting moment of existence, all encapsulated in a single, cohesive framework. This is the quest for the theory of everything. It's an idea so bold, so ambitious, that it feels almost mythological, and yet for physicists, it represents the ultimate prize, a final answer to the grandest question of all. Why does the universe behave the way it does? To understand this quest, we need to travel back to a time when physics was divided into kingdoms, separate realms ruled by separate laws. On one side was the world of the very large galaxies, black holes, and the curving fabric of space-time, a world governed by Albert Einstein's general theory of relativity, where gravity is not a force pulling objects together, but the very bending and warping of space and time itself. On the other side was the world of the very small particles fields and quantum probabilities, a chaotic, jittery realm described by quantum mechanics, where electrons exist in clouds of possible, where particles can tunnel through barriers, and where certainty is replaced by probability. Both theories are breathtakingly successful. General relativity explains the movements of planets and the warping of light by distant stars. With exquisite precision, quantum mechanics underpins our understanding of chemistry, material science, and the very functioning of the devices you're using to hear these words, and yet they cannot coexist when we try to combine general relativity and quantum mechanics. The mathematics fall apart, equations spit out, infinities, paradoxes arise, and the beautiful logic of both theories breaks down. It's as if we're trying to stitch two incompatible maps together, one describing vast continents, the other detailing the microscopic streets of a single city. Both maps are correct in their own domain, but together they clash. The quest for a theory of everything is the quest to bridge this divide, to find a single framework that can seamlessly describe the universe at all scales, from the swirling gravity wells of black holes to the restless quantum froth of subatomic particles. One of the most promising candidates for this ultimate theory emerged in the late 20th century, and it came with a rather poetic name: string theory. At its core, string theory proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings, infinitesimal loops of energy, each vibrating at a different frequency, just as the strings of a violin produce different musical notes depending on how they vibrate. These cosmic strings produce different particles depending on their vibration patterns: electrons, quarks, photons. They are not distinct objects, but different notes played on the same universal instrument. It's a beautiful idea, elegant, harmonious, and yet it comes with a cost. String theory doesn't work in our familiar universe of 3 dimensions of space and 1 of time. It demands extra dimensions, hidden layers of reality curled up so tightly that we can't see them. 10 dimensions, maybe 11 realities stacked upon realities, like hidden pages folded within the universe. For decades, physicists have pursued string theory, crafting intricate mathematical models, searching for experimental hints. But so far, the evidence remains elusive. The strings, if they exist, are far too small to detect. With our current technology, the extra dimensions remain stubbornly hidden, tucked away in the folds of space-time. And so, while string theory remains a frontrunner, it is not the only contender. Another theory, called loop quantum gravity, takes a different approach. Instead of strings, it proposes that space-time itself is not smooth and continuous, but made of tiny, indivisible loops, like pixels on a screen. These loops form the fabric of reality, discrete building blocks of space and time. Both theories offer tantalizing glimpses into the same fundamental question: what is reality made of? But perhaps the problem isn't with our theories, but with our assumptions. What if the universe isn't a tidy set of mathematical laws waiting to be discovered? What if our need for a single, elegant theory is nothing more than a reflection of our human desire for simplicity and beauty. The search for a theory of everything isn't just about physics, it's about philosophy. It's about whether the universe needs to make sense to us or whether it simply is. Are we chasing a mirage, or are we genuinely on the verge of the most profound discovery in the history of science? For physicists like Stephen Hawking, this question was deeply personal. Hawking spent much of his life searching for a unifying theory driven by the belief that humanity could one day know the mind of God, and yet, as he grew older, Hawking began to doubt whether such a theory was even possible. Perhaps the universe is not governed by a single unifying principle, but by a patchwork of overlapping laws, a mosaic rather than a monolith. And so the search continues in particle colliders buried deep underground, in equations scrolled across whiteboards late into the night, in the faint whispers of gravitational waves rippling through space-time. Every discovery brings us closer, but also reveals how far we still have to go. But maybe the beauty of the theory of everything isn't in the answer, it's in the pursuit. It's in the audacity of asking the biggest question imaginable. It's in the realization that we fragile creatures on a tiny blue planet orbiting an ordinary star dare to believe that we can understand the universe itself, whether or not we ever find the theory of everything. The quest itself has transformed us. It has shown us the staggering complexity of reality, the harmony hidden in chaos, and the profound beauty of the cosmos. And perhaps one day someone will write down a single equation, a few lines of symbols on a chalkboard that will capture it all: the stars, the galaxies, the particles, the fields, every fleeting moment, every infinite expanse, a cosmic Rosetta Stone, unlocking the deepest secrets of existence. But until that day comes, the question remains: is there a final answer to everything? Or will the universe always keep a part of itself hidden from view, an eternal enigma waiting in the silence of space? In the end, the theory of everything is not just about understanding the universe, it's about understanding ourselves. Why we ask, why we wonder, why we look at the night sky and feel the pull of something vast, something unknowable, and yet something deep, deeply familiar. Nature constants. Nature often feels like it operates with unshakable precision. Stars ignite, planets orbit, and atoms vibrate in predictable patterns, all governed by a set of fundamental constants. These are the universal numbers etched into the very fabric of reality: the speed of light, the gravitational constant, the charge of an electron. They are the scaffolding upon which the universe builds its intricate architecture. But what if these constants aren't constant at all? This question might seem almost heretical. After all, the universe relies on these values being fixed. If the gravitational constant changed even slightly, stars might not ignite, galaxies might not form, and life as we know it would be impossible. The universe would unravel into chaos. Yet, some physicists suspect that these constants may not be as immovable as we assume, and at the heart of this suspicion lies one of the strangest hypothetical particles ever conceived: the axion. The axion was first proposed to solve a problem within quantum chromodynamics, the theory describing how quarks interact via the strong nuclear force. according to the mathematics. This force should violate something called CP symmetry, a principle stating that if you swapped particles for antiparticles and flipped the universe in a mirror, the laws of physics should remain unchanged. But in the real world, the strong force doesn't seem to violate the symmetry at all. It's too perfect, too balanced. This mismatch is called the strong CP problem, and the axion was born as a theoretical patch to fix it. But as often happens in physics, the axion turned out to be more than just a mathematical band-aid. If axion exist, they wouldn't just fix the strong force, they might. Theory of everything also play a key role in one of the greatest cosmic puzzles of all time. Dark matter axions, with their ghostly properties and incredibly weak interactions with ordinary matter, are prime candidates for the invisible mass holding galaxies together. Yet the axion's potential doesn't stop there. These elusive particles might also influence the fundamental constants of nature themselves. In certain theoretical models, axions could act like cosmic dials subtly tuning Con, such as the fine structure constant, which dictates how light interacts with charged particles. If axion can vary across space and time, then constants might not be so constant. After all, astronomers have already begun searching for evidence of these cosmic dials. They look at distant light from quasars, ancient beams stretched across billions of years, and countless light years of space. If the fine structure constant was slightly different billions of years ago, the signature would be etched into this ancient light, and in some studies, hints have emerged tiny deviations, anomalies that refuse to disappear completely. But these findings are not yet definitive. The search for axions continues in laboratories buried deep underground, shielded from cosmic noise. Scientists use magnetic fields and exquisitely sensitive detectors to try and watch the faintest whisper of these ghost particles. Each experiment brings us closer to an answer, but so far, the axion remains elusive, a faint silhouette on the horizon of our understanding. If axions are found, they would not only address long-standing problems in particle physics and cosmology, but also challenge our assumption of an unchanging universe. They could reveal that the constants of nature, which seem so fundamental and eternal, are dynamic properties shaped by the universe itself. For now, the search continues across distant starite, within magnetic traps, and through mathematical models. The axion remains one of the most tantalizing possibilities in modern physics, and with every experiment, every flicker of anomalous data, we inch closer to either discovering this elusive particle or rewriting the very rules we thought the universe was built upon. The Pioneer Anomaly, far beyond the planets of the Pioneer Anomaly solar system, in the cold and silent void where sunlight fades into eternal darkness. Two lonely spacecraft drift through the cosmos, the Pioneer 10 and Pioneer 11. Probes built by human hands, launched on fiery rockets in the early 1970s, were among the first emissaries of Earth to venture into interstellar space. Their mission to explore the outer planets and carry our curiosity beyond the edges of the known solar system. But in the quiet decades that followed their launch, scientists noticed something strange, a faint whisper in the data, an imperceptible tug, as if some invisible force was ever so slightly pulling the probes back toward the sun. This was the Pioneer Anomaly, a cosmic riddle that would baffle scientists for decades and challenge our understanding of gravity itself when Pioneer 10 was launched in 1972, followed by Pioneer 11. A year later, the probes carried with them golden plaques etched with humanity's message to the stars. They journeyed past Jupiter and Saturn, sending back breathtaking images and groundbreaking data. Eventually, their trajectories took them outward, beyond the realm of planets, into the void where the sun is just another distant star. Everything seemed normal. The laws of physics, meticulously calculated by scientists, had predicted their paths with extraordinary precision. But as the years passed, radio signals from the probes revealed a puzzling discrepancy. The spacecraft weren't exactly where they were supposed to be. Both Pioneer 10 and Pioneer 11 were drifting ever so slightly off their expected course, moving slower than they should have been, as if an invisible hand was gently pulling them back. It wasn't much. Just a tiny deceleration, about 110 billionth of an m squared, insignificant on human scales, but in the unforgiving precision of space. Exploration, this anomaly stood out like a beacon. It was consistent, persistent, and deeply mysterious. At first, scientists questioned the data. Could it be an error in the instruments, a glitch in the calculations? But as more data rolled in, the anomaly refused to disappear. It became a stubborn fact, an inconvenient riddle that demanded an answer. Could this discrepancy point to new physics? Was there an unknown force operating in the void of space? Or perhaps most unsettling of all, could our understanding of gravity itself be incomplete? Theories began to emerge. Some suggested that the anomaly was caused by dark matter, the invisible substance that makes up most of the universe's mass. Others speculated about modified gravity theories, exotic tweaks to Einstein's equations that might explain the strange tug on the probes. And then there were the wild ideas, hidden dimensions, cosmic drag forces, or even interactions with the quantum fabric of space-time itself. But before rewriting the physics textbooks, scientists needed to rule out the mundane explanations. Could the anomaly be caused by heat? The Pioneer probes, after all, carried radioactive power sources, and heat emitted from these systems could in theory create tiny thrusts that might explain the drift. This wasn't an exciting answer. It was more engineering than cosmic revelation, but science thrives on rigor, not romance. Years of painstaking analysis followed. Researchers dug into telemetry data, modeled thermal emissions, and calculated the effect of every photon of heat leaving the spacecraft, and slowly, a picture began to emerge. It turned out that heat radiating unevenly from the back of the probes was creating a minuscule but persistent recoil effect, like the faintest puff of air nudging the spacecraft ever so slightly backward in 2012. After decades of debate, the anomaly was largely explained. The mysterious deceleration wasn't caused by dark matter, exotic physics, or hidden dimensions. It was heat, plain, ordinary heat. The universe, it seemed, hadn't broken its own rules after all. But was this the end of the story? Not entirely. The resolution of the Pioneer anomaly wasn't just about solving a cosmic puzzle. It was a testament to the power of science itself. It showed how patient investigation, grounded in data and careful analysis, can illuminate even the most stubborn mysteries. It reminded us that the universe doesn't yield its secrets easily, and sometimes the answer isn't in grand, sweeping theories, but in the tiniest details. Yet even with the anomaly explained, the legacy of Pioneer 10 and Pioneer 11 endures. These silent travelers continue their lonely drift through the stars. Their signals have long faded. The systems have gone quiet, but they remain out there. Messengers from a small blue planet orbiting an ordinary star, carrying our curiosity and our questions into the infinite night. And somewhere, perhaps in the distant future, another civilization might stumble upon one of these probes. They might see the golden plaque with its etched diagram of a man and woman and wonder about the strange creatures who sent it. They might even ask themselves what drove these beings to launch such fragile machines into the vast cold dark. The Pioneer anomaly began as a question about physics, but it ends as a reflection on something deeper. It's about our insatiable need to explore, to question, and to understand. It's a reminder that every mystery we solve brings us closer to the heart of reality, and every answer leads to more questions. The journey of the Pioneer probes isn't just a story of space exploration. It's a story of humanity's enduring curiosity, and as they sail through the endless dark, they remind us of something profound. The universe is vast, mysterious, and waiting, always waiting for us to ask the next question. Neutrino oscillations and anomalies in the grand orchestra of the neutron lifetime. Discrepancy cosmos. Neutrons are the quiet performers, small, unassuming particles tucked inside the heart parts of atoms, playing a crucial role in the structure of matter. Without them, stars wouldn't shine, atoms wouldn't hold together, and the universe as we know it wouldn't exist. But there's something deeply puzzling about these humble particles when freed from the safety of an atomic nucleus. Neutrons face an existential crisis. They decay quietly, inevitably transforming into protons, electrons, and neutrinos in a process called beta decay. But here's the strange part. No one can agree on how long they take to do it. It's called the neutron lifetime discrepancy, and it's one of the most stubborn and perplexing mysteries in modern physics. Two different methods for measuring the lifetime of a free neutron, methods that should agree perfectly consistently, producing answers that differ by about 9 seconds. 9 seconds may not sound like much, but in the precision-driven world of particle physics, it's a chasm. A chasm wide enough to hint at something deeper, something hidden in the laws of nature. Could it be a flaw in our experiments, a subtle effect we've overlooked, or could it be evidence of something truly extraordinary, like the existence of unknown physics just beyond our reach? To understand the puzzle, we need to shrink down, to dive into the invisible world of subatomic particles, where force is stronger than anything in our daily experience, hold protons and neutrons together. Inside atomic nuclei, neutrons are like cosmic glue. Inside a nucleus, they're stable, bound tightly alongside protons by the strong nuclear force. But when you set a neutron free, when it's no longer cradled by the protective shell of its atomic family, it becomes unstable, like a clock ticking toward inevitability. On average, a free neutron lives for about 15 minutes before decaying into a proton, an electron, and an antineutrino. But how do we measure something so fleeting, so small, and so utterly invisible to the naked eye? Physicists have devised two primary methods: the bottle method and the beam method. In the bottle method, scientists trap neutrons in a carefully designed magnetic or gravitational bottle, a kind of invisible cage that keeps the particles confined over time. They count how many neutrons remain and calculate the average time it takes for them to decay. The bottle method gives a neutron lifetime of about 8799 seconds in the beam. Method physicists take a very different approach. They fire a beam of free neutrons through a detector and measure how many protons are produced from neutron decay over time. Using this data, they calculate the neutron's lifetime indirectly. The beam method, however, instantly returns a slightly longer lifetime, around 888 seconds. These two methods should align. The universe doesn't have one set of rules for neutrons trapped in a bottle and another for neutrons in a beam. But no matter how many times the experiments are repeated, the discrepancy persists for years. Scientists have checked and rechecked their calculations. They've upgraded their equipment, refined their techniques, and eliminated every obvious source of error, and yet the nanosecond gap remains hanging in the air like an unsolved riddle. At first glance, it might seem like a technical problem, an experimental inconsistency waiting to be ironed out, but some physicists are beginning to suspect something far more profound, that this discrepancy could be a sign of new physics lurking in the shadows. One idea is that neutrons might not always decay into the familiar trio of proton-electron and antineutrino. Instead, they might occasionally decay into something else, something invisible, something we've never detected. Perhaps a neutron sometimes vanishes into a hidden particle like a dark matter candidate. If this were true, it would mean that every neutron lifetime experiment is unintentionally glimpsing a doorway into the unknown, a fleeting interaction with a hidden sector of the universe. Other physicists suggest that the discrepancy might point to a deeper flaw in our understanding of the weak nuclear force, the force responsible for neutron decay. Could it be that our equations, our assumptions, are missing a term, a correction, an insight? The implications are staggering. If neutrons can decay into dark matter, it would not only solve the neutron lifetime puzzle, but also shine a spotlight on one of the greatest mysteries in modern cosmology, the true nature of dark matter itself. But extraordinary claims require extraordinary evidence. Right now, the neutron lifetime discrepancy remains a stubborn anomaly, an itch on the surface of physics, refusing to go away. New experiments are being designed with even tighter controls and even greater precision. Physicists are building more sensitive neutron traps, more refined beams, and detectors capable of capturing the faintest whispers of particle interactions. And while these experiments run, the universe waits, because the neutron lifetime isn't just a quirky detail for particle physicists to argue about. It's a cornerstone of our understanding of the cosmos. The exact lifetime of a free neutron influences the abundance of elements created in the Big Bang nucleosynthesis, the cosmic recipe that cooked up hydrogen, helium, and lithium in the first few minutes after the Big Bang. Get the neutron lifetime wrong, and our entire model of the early universe starts to wobble. So here we are, standing at the edge of an unanswered question. Two measurements, two answers. One mystery somewhere buried in those 9 seconds is a clue, a flicker of something extraordinary waiting to be understood. Perhaps the answer lies hidden in the particles we cannot see, in forces we cannot yet measure, or in the uncharted corners of physical law, or perhaps, like so many great mysteries in science, the truth is waiting just beyond the reach of our instruments, waiting for the next leap in technology, or for a mind bold enough to see the pattern hidden in the noise. For now, neutrons continue their silent dance in bottles and beams, in the hearts of stars and the depths of laboratories. They decay and vanish, ticking out their fleeting life, expand against the vast backdrop of time. Somewhere in those ticks, those tiny invisible seconds, is an answer, and if we can find it, it just might change everything we thought we knew about the universe. Neutrino oscillations and neutrino oscillations and anomalies in the quiet corners of the universe, where starlight fades into the endless dark and particles drift silently across the void. There exists a mystery so profound that it challenges our very understanding of reality. It begins with the neutrino, a particle so elusive, so ghost-like, that trillions of them are passing through your body right now, without leaving a trace. Neutrinos are cosmic phantoms, whispering secrets from the hearts of stars, from exploding supernova, and from the most violent corners of the cosmos. And yet, despite their abundance, despite their omnipresence, they remain one of the greatest enigmas in physics. Our story begins in the 1930s with a problem that haunted physicists like Wolfgang Pauli. During experiments with radioactive decay, scientists noticed something odd. The energy from decaying particles wasn't adding up. It was as if a portion of the energy was simply disappearing. Pauli, desperate to preserve the sacred laws of physics, proposed a radical idea. What if there was an invisible particle so small and so reluctant to interact with matter that it simply slipped away undetected during radioactive decay? He called it the neutrino, meaning little neutral one in Italian. It was a bold prediction, and at the time it sounded almost impossible to verify. Neutrinos are uncharged, nearly massless, and interact so weakly with matter that they can pass through a light year of lead without slowing down. But in 1956, physicists Clyde Cowan and Frederick Raines finally detected them in a nuclear reactor experiment. The ghostly particles were real, but this was just the beginning. Over the following decades, neutrinos would reveal themselves to be far stranger than anyone had anticipated. Physicists discovered that there were not one, but 3 types of neutrinos, each associated with a different particle: the electron neutrino, the muon neutrino, and the 2 neutrino. And here's where the mystery deepens. Neutrinos, it turns out, can change from one type to another as they travel through space. This phenomenon is known as neutrino oscillation. Imagine firing a beam of neutrinos. Across the universe, You might start with a pure stream of electron neutrinos, but by the time they reach a detector on the other side, some of them have transformed into mu neutrinos and others into 2 neutrinos. It's as if these particles can't decide what they want to be. They exist in a state of perpetual identity, crisis, shape-shifting as they move through the cosmos. But here's the catch. According to the standard model of particle physics, neuter inos should be massless. The theory insists that they should zip through space at the speed of light unburdened by mass. Yet neutrino oscillations require them to have mass. Without mass, they couldn't change flavors. They would be frozen in their initial state. This means that neutrinos are living proof that the standard model is incomplete. They are cracks in the foundation of one of our most cherished theories. But the story doesn't end there. Neutrino experiments have uncovered anomalies. Strange, unexplained results that hint at something even deeper. Something we don't yet understand. Take, for example, the solar neutrino problem. The sun, powered by nuclear fusion in its core, should produce an enormous number of electron neutrinos. Physicists built massive underground detectors like Super Cameo Candy in Japan and Snow Sudbury Neutrino Observatory in Canada to catch these fleeting visitors from our star. But when the data came in, there was a problem. Only about 1/3 of the expected electron neutrinos were being detected. It was as if 2/3 of them had simply vanished on their journey from the sun to Earth. The answer turned out to be neutrino oscillation as the electron neutrinos traveled through space. Many of them were transforming into Moon and to Neut-OS types that the detectors at the time weren't sensitive to. The mystery was solved, but the implications were staggering. Neutrinos not only have mass, but they also behave in ways that defy our standard understanding of particle physics. And then there are the reactor neutrino anomalies in experiments designed to study neutrinos produced by nuclear reactors. Scientists found something puzzling: a persistent shortage of detected neutrinos compared to theoretical predictions. This discrepancy has led some physicists to propose the existence of a fourth type of neutrino, a sterile neutrino, unlike the 3 known types. Sterile neutrinos wouldn't interact with matter at all, except through gravity. They would be even more ghostly, more intangible than their already elusive cousins. If sterile neutrinos exist, they could answer some of the biggest questions in physics. They might be linked to dark matter, the invisible scaffolding holding galaxies together. They might hold clues to the universe's matter, antimatter, asymmetry, explaining why our cosmos is filled with matter rather than being annihilated into pure energy. But finding sterile neutrinos is like trying to hear a whisper in a hurricane. Experiments like Diabe Minos and Ice Cube have searched for their faint signatures, and while hints have appeared, definitive proof remains elusive. Every discovery about neutrinos seems to peel back one layer of the mystery only to reveal another beneath it. Neutrinos are messengers from the hidden realms of the universe. They're born in the fiery hearts of stars, in the cataclysmic explosions of supernova, and in the depths of nuclear reactors. They pass through planets, stars, and even black holes, carrying with them secrets about the most extreme conditions in nature. They are both incredibly ordinary. They flood the universe in staggering numbers, and profoundly strange, refusing to fit neatly into our theoretical frameworks. But perhaps the most remarkable thing about neutrinos isn't just their ghostly nature or their shape-shifting identities. It's the questions they force us to ask. Why do they have mass? Are there more types waiting to be discovered? Could they be connected to the dark matter that fills the cosmos, in every detector buried deep underground, in every beam fired across continents? Physicists are listening for answers. They're watching for faint flashes of light, tiny ripples in their instruments that could reveal another piece of the puzzle. The universe, it seems, speaks to us in whispers and neutrinos. These silent, ghostly messengers are some of the quietest voices of all, but if we can learn to listen, if we can decipher their faint signals, they might just tell us a story, unlike any we've ever heard a story about, the deep structure of reality, the hidden symmetries of the cosmos, and perhaps, just perhaps, the ultimate fate of the universe itself. Proton decay. Decay in the quiet depths of time, beneath the surface of reality, where protons and neutrons stitch the universe together. A silent clock may be ticking. It's a clock so slow, so faint, that it's almost imperceptible, a countdown woven into the fabric of every atom in your body, every molecule of water, every star in the sky. It's the question of proton decay, one of the greatest unsolved mysteries in modern physics. Protons are the bedrock of matter. They form the hearts of atoms, anchoring electrons in their orbits and giving structure to everything we see, in touch for all practical purposes. Protons are eternal. They don't age, they don't wither, and they don't fall apart, at least not within the limits of our current understanding. But what if that isn't true? What if, given enough time, even the proton, this cornerstone of reality, will crumble into something else? If protons decay, it means something profound. The universe is not built on permanence. Even the most fundamental pieces of matter have an expiration date, a moment when their structure will fail and they'll dissolve into smaller, more ethereal particles. It means that everything, every galaxy, every star, every atom will one day fade away into nothingness. But here's the twist: despite decades of searching, no one has ever seen a proton decay to understand why this question matters so deeply. We need to go back to the fundamental building blocks of reality, the standard model of particle physics. This model is our best attempt at describing the universe at its smallest scales. It tells us about quarks and leptons, about photons and gluons, about the invisible threads of force that hold matter together. And according to this model, protons should be stable forever. But physics doesn't stop at the standard model. There are theories that go further, theories that try to unite the fundamental forces of nature, gravity, electromagnetism, the weak force, and the strong force, into one elegant framework. These are called grand unified theories, or GUTS. And in these theories, protons are not eternal. They can, in fact, decay. Imagine a proton sitting quietly at the center of an atom in its decaying moment, an event so rare it might only happen once every 10 to the power 34 years. It would suddenly transform, spitting out a cascade of exotic particles. The exact details depend on the theory you choose, but one common prediction is that a proton would decay into a positron, a positively charged electron, and a neutral p, which itself would quickly decay into gamma rays, bursts of light. A single proton's death would be a faint flicker, an almost imperceptible sigh in the darkness, but multiplied across every proton, in every atom in the universe, it would mark the slow unraveling of matter itself. But here's the problem: we've never seen it happen. Physicists have built enormous underground laboratories to search for proton decay, shielding their detectors from cosmic rays and background noise. Take the Super Came, an experiment in Japan, a giant tank filled with 50,000 tons of ultra-pure water buried deep beneath a mountain. It's surrounded by thousands of sensitive light detectors, watching, waiting, hoping to see the faint telltale glow of a proton's final breath. Years have passed, decades even, and yet nothing does this mean protons are truly eternal. Or are we just not looking in the right way? Maybe our theories are incomplete. Maybe protons do decay, but in ways we haven't anticipated, or on timescales so vast they stretch far beyond our ability to observe them. The search for proton decay isn't just about particles, it's about the fate of the universe. If protons are stable, then matter could in principle exist forever. Stars might fade, galaxies might scatter, but the protons would endure a silent, eternal sea of particles drifting in the cosmic dark. But if protons decay, then the universe has an endgame. In the unimaginably distant future, long after stars have burned out and black holes have evaporated, the final act of the cosmos will be the slow, quiet decay of protons, atom by atom, molecule by molecule. The very substance of reality would disintegrate into radiation, fading into a thin, cold mist of photons and neutrinos. The stakes are enormous, and the timeline is inconceivably vast. But here's the strange beauty of physics. Even when we're dealing with timescales longer than the age of the universe itself, even when the signals we're searching for are faint glimmers on the edge of detectability, we still look. Why spend decades, billions of dollars, and countless hours chasing something so elusive, so ethereal? Because answering this question isn't just about protons. It's about our universe, our reality, and our place within it. If protons decay, then the cosmos isn't static. It's dynamic, changing, evolving on scales far beyond our human lifetimes. And if protons are eternal, then we have to ask why, what makes them so perfectly stable in a universe that seems to favor chaos and change every experiment that runs in the silence of underground laboratories, every photon captured by a detector, every theory scribbled on a physicist's chalkboard. It's all part of a larger story, a story about the most basic rules of reality, about whether the universe itself has a final chapter or whether it will drift endlessly into an unchanging eternity, somewhere buried in the noise of our experiments, hidden in the equations we have yet to solve. The answer is waiting. Maybe it's in a single flicker of light deep underground, a faint whisper from a dying proton. Or maybe it's in a theory we haven't thought of yet, a new framework that will reshape everything we know for now. The protons in your body remain stable. They sit quietly holding your atoms together, building the structures of your reality. but somewhere, perhaps in a distant star, perhaps deep underground, perhaps in a single part particle floating through the void, one proton might already be ticking away its final seconds. The cosmic lithium problem in the aftermath of the Big Bang, the cosmic lithium decay universe was a swirling cauldron of unimaginable heat and density. Protons, neutrons, and electrons danced in chaos, colliding and fusing in a cosmic crucible that set the stage for everything we see. Today, as the universe cooled, something miraculous happened, a process known as Big Bang nucleosynthesis. In this brief window, just minutes after the birth of time itself, the first light elements were forged: hydrogen, helium, and a delicate trace of lithium. These elements would become the foundation for stars, galaxies, and eventually life itself. But amidst this elegant story of creation, something doesn't quite add up. Enter the cosmic lithium problem, a riddle that has defied explanation for decades. According to our most reliable models of the early universe, there should be 3 times more lithium in the cosmos than what we actually observe. Somehow, somewhere, this delicate metal either disappeared, was destroyed, or never formed in the quantities we expected. It's a paradox that GW's at the edges of cosmology, hinting at either a gap in our understanding of nuclear physics or something far stranger lurking in the fabric reality. To understand the issue, we need to revisit those first few minutes of cosmic history. Hydrogen, the simplest and most abundant element, formed almost effortlessly. Helium followed its formation, governed by well-understood nuclear reactions. But lithium, the third element on the periodic table, was a far more delicate player in this primordial dance. It formed under extremely specific conditions, requiring a careful balance of temperature, pressure, and particle interactions. Even a slight deviation could disrupt its production. Our models predict that about 1 lithium atom should have formed for every 10 billion hydrogen atoms. But when astronomers peer into the oldest stars, ancient stellar relics that have remained largely unchanged since the dawn of time, they consistently find only a third of the expected lithium. It's as if 2/3 of the lithium that should exist simply vanished for decades. Scientists have wrestled with this anomaly. Some propose that the lithium was somehow destroyed inside, stars burned away in their fiery cues. But this explanation has its limits. Many of the stars studied are ancient and relatively cool, unlikely to have processed their lithium so thoroughly. Others suggested that lithium might have been diluted in the outer layers of stars hidden from our telescopes. Yet even the most advanced observations struggle to reconcile the discrepancy. In 2012, researchers turned their attention to exotic physics. Could it be that unknown particles, perhaps remnants from the early universe, interfered with lithium production? The idea of beyond the standard model physics began to surface, an unseen factor that disrupted the delicate nucleosynthesis process. Some theorists even proposed that dark matter particles played a role, subtly altering the nuclear reactions responsible for lithium's creation. Then there's the tantalizing possibility that our understanding of the early universe itself is incomplete. What if Big Bang nuclear synthesis didn't proceed quite as we imagined? What if an unknown phase transition, a cosmic event hidden in the earliest moments of time, change the rules of the game. These are not casual speculations. They represent cracks in our otherwise robust understanding of cosmology. But the cosmic lithium problem doesn't just reside in the distant past. Lithium is crucial for life as we know it. It's a key element in modern technology, essential for batteries that power our devices. More intriguingly, lithium plays a role in brain chemistry, with lithium salts used as mood stabilizers in treating certain mental health conditions. How strange it is to think that this humble element, essential for both technology and biology, carries with it a cosmic mystery, and so we're left with an unresolved enigma, the universe. Despite all its elegance and mathematical precision, still hides secrets in plain sight. The cosmic lithium problem isn't just about a missing element, it's a reminder of our limits, a gap in our cosmic map that whispers of something we don't yet understand. Maybe the solution lies in new physics waiting to be discovered in the cold collisions of particle accelerators, or perhaps it's hidden in the light of distant stars waiting for more advanced telescopes to reveal their secrets. For now, lithium remains an elusive puzzle piece in the grand mosaic of the cosmos. But isn't that what makes science beautiful? The unanswered questions, the mysteries that pull us forward. The cosmic lithium problem is more than just a discrepancy. It's a doorway, a clue that somewhere deep in the fabric of reality, something profound awaits our discovery, and one day, perhaps not too far from now, we'll find it. Heat. Death of universe, the universe. Heat, death of universe, feels alive. Stars burn brightly, planets orbit in delicate balance, and galaxies swirl across the cosmic tapestry in grand sweeping arcs. From the smallest atom to the largest black hole, energy flows, motion persists, and time marches forward. But one day it will all stop. Every star will flicker out, every galaxy will grow cold, and every trace of motion, every spark of energy will fade into silence. This is the heat, death of the universe, a haunting vision of the cosmos's final chapter, a universe where nothing happens, nothing changes, and nothing will ever again. But how could such a fate come to pass? How does a universe filled with fiery stars and vibrant galaxies wind down into an eternal, frozen stillness? To understand, we need to talk about entropy. In the mid-19th century, physicists like Rudolf Clausius and Ludwig Boltzmann introduced the concept of entropy, a measure of disorder in a system. Imagine a cup of hot coffee sitting in a cold room. Over time, the heat from the coffee spreads into the air. Eventually, the coffee and the room will reach the same temperature, and heat will stop flowing. The system has reached thermal equilibrium. The universe operates on the same principle. Energy always flows from areas of high concentration to low concentration, from hot to cold, from ordered to disordered, and every time energy flows, a little bit of it becomes unusable, locked away in forms that can no longer do work. This is the second law of thermodynamics, one of the most fundamental rules of physics. Entropy always increases in a closed system, and the universe is the ultimate closed system. Right now, our universe is in a state of incredible activity. Stars fuse hydrogen into helium, releasing immense in energy. Planets absorb starite. Black holes consume matter. Energy flows in endless cycles, driving the dance of galaxies and the light of stars. But it won't last forever. Stars are not eternal. In about 100 trillion years, the last stars will burn out. These will be red dwarfs, small, cool stars that burn their fuel with agonizing slowness, but even they will eventually exhaust their hydrogen when the final star flickers. Into darkness, a new era begins. The degenerate era, black holes, neutron stars, and white dwarfs will dominate the universe. These objects are remnants of stars. Stellar corpses, they don't shine. They don't create, they simply exist. But even they won't last forever, over unimaginably long time. Scales. White dwarfs will cool to become black dwarfs, frozen, husks of carbon and oxygen drifting through space. Meanwhile, black holes will slowly evaporate through a phenomenon called Hawking radiation in the 1970s. Physicist Stephen Hawking discovered that black holes aren't perfectly black. They emit tiny amounts of radiation, losing mass in the process over 10 what or 100 years a number. So vast it defies comprehension. Every black hole in the universe will evaporate into nothing. What's left after that? Only particles, protons, electrons, neutrinos drifting through an endless, lightless void. And even these particles might not be eternal. Some theories suggest that protons could eventually decay, leaving behind a universe filled with nothing but low energy, photons, and wisps of radiation. No stars, no planets, no black holes, just a thin, cold mist of particles spread across an infinite void. At this point, the universe will have reached maximum entropy. Every last bit of usable energy will have been distributed evenly. There will be no gradients, no flows of heat or energy, no chance for complexity or structure to arise. Time in any meaningful sense will lose its purpose because time, as we understand it, is tied to change. And in a universe where nothing changes, does time even exist? This is the heat. Death. A universe where everything has settled into the final, inevitable stillness. But there's a strange beauty to this grim fate for billions of years. Stars burned brightly, galaxies danced, and life, brief and fragile, emerged to witness it all. The universe was a stage, and for a fleeting moment, it was filled with light, sound, and movement. But nothing lasts forever, and perhaps in some distant corner of this fading cosmos, there will be one final spark, a photon escaping from the last decaying particle, racing through an endless night, carrying with it the faintest echo of a universe that once was vibrant and full of life. The heat death of the universe is not a dramatic end. There will be no explosion, no cataclysm, no grand finale, just a slow, relentless fading until everything is quiet. The story of the universe began with a bang, but it will end in a whisper, a long, cold, silent sigh stretched across eternity.